Place.
Yeah, the battery's pretty high.
Okay, yeah. Yeah, replacement. There's a couple.
This is the first session of the day on mercury and POPs. I'm Leonard Levin of Emory, Palo Alto, California. Our first speaker is Hannah Horowitz of Harvard. I'll be holding up timeout and waving them when it gets closer to the stop time. So, thank you. Hannah, begin.
Thanks. Okay. Hi, everyone. I'm Hannah Horowitz, and today I'll be talking about my recent work looking at revising the atmospheric mercury oxidation mechanisms in geochem. And I'd like to start off by thanking all of my co-authors. Okay, so two of the most robust observational constraints that we have for atmospheric mercury redox cycling are the total atmospheric burden, which based on observations ranges from about 4,600 to 5,600 megagrams, and the lifetime of elemental mercury against oxidation followed by deposition, which ranges from a few months to a year. And this is based on the interhemispheric gradient of elemental mercury concentrations. And I'm showing here a figure from Chris Holmes' 2010 paper, which was the last major update in mercury oxidation chemistry, where it introduced bromine atom as the major oxidant of mercury. And this was a really revolutionary update, and it managed to stay within the two major observational constraints that I just mentioned. So the burden was about 5,000 megagrams, and the lifetime of elemental mercury against oxidation followed by deposition was 10.4 months. But now we have some more recent information that suggests that there are additional oxidation reactions that were missing from this previous work, and that the bromine concentrations might have been too low as well. And then we also have reason to believe that we should re-examine this reduction term as well. So we need to update the model to be consistent with what we know from new observations, but how will this affect our ability to match these observational constraints? So today I'm going to propose some changes that I think should be made to the standard mercury model in geochem, starting with the bromine field. So in the standard V902 of geochem, we're using the bromine fields from Justin Perella. And we've already heard from Johan Schmidt about his new bromine model in geochem, which matches better with observations. And so here I'm just showing the change in annual mean, zonal mean concentrations between the two versions, with the new bromine on the right and the V902 on the left. And so overall, tropospheric bromine is about 70% higher in the troposphere. And so this will serve to decrease the burden of mercury and the lifetime, because it's increasing the oxidation and allowing that mercury 2, which has a shorter lifetime, against deposition. In V902, there also was strong in-plume reduction. So essentially, this means that 75% of the emitted oxidized mercury from power plants is immediately reduced to mercury 0. And I'm proposing that we should take this out. And this is for a couple of reasons. First, there's some recent work that Yangshu Zhang will probably be talking about later today, where he found that if you actually correct the emissions speciation, taking into account new control technologies, this almost completely compensates for this change in speciation that we had initially put in. And in addition, we have a lot more observations within plumes that suggest that in-plume reduction only happens sometime under very specific conditions, and overall is a much lower magnitude than the 75%. So by not including in-plume reduction, we're essentially changing the speciation of the emissions to have a lot more oxidized mercury. And so then this will lead to more faster wet deposition of mercury because of the shorter lifetime of mercury 2. And so the burden will go down again because of this change. Also in V902, we had in-plume aqueous photoreduction of mercury. And again, I'm proposing that I think we should take this out. And there's a couple reasons. One is that we still do not have a mechanistic understanding of what is actually going on in this reaction. And in addition, if we are to include aqueous mercury 2 photoreduction, it would follow that we should also include this in sulfate aerosol that occurs in the upper troposphere and lower stratosphere. But if we have mercury 2 being reduced in this region, this is not consistent with our understanding of the vertical profile of mercury speciation, where we have an increase in mercury 2 in this region and a decrease in mercury 0. So this doesn't seem to be consistent with our understanding of mercury. And then finally, the most major change and focus of my talk is revisiting the oxidation mechanism itself. So in the V902, we have oxidation initiated by the bromine atom, and then the second step of oxidation going from mercury 1 to mercury 2 only involves bromine atom and OH. And so I'm including additional oxidation reactions and also updating the rate coefficients for these reactions based on new information in the literature. So I'm showing here the previous general oxidation mechanism. So where bromine is initiating the oxidation, and then in this final step going to mercury 2, you can have bromine or OH. And based on newer theoretical chemistry work, I'm including additional oxidants here that have been shown to be viable in the second step as well as in the first step. And then I'm also including in-cloud aqueous oxidation. And then updating the rate coefficients. So some of these rates have been improved. And in addition, I'm also using rates within the uncertainty ranges that will lead to a lower overall oxidation rate because I'm adding all of these new oxidants. So these are both updated because of new kinetic information and within the lower range of uncertainty. So overall, I'm having smaller rate coefficients, but more oxidants. So we'll see later how this affects the overall burden in lifetime. So very quickly, some results. So when I include all of these new oxidants, you can see that, in fact, NO2 and HO2, because they are so much more abundant, really dominate over the original oxidants that were included in the second step. And on the right, this is a zonal mean plot of mercury oxidation, mercury 2 production. And so because of the new bromine fields and the additional oxidants, we see more oxidation in the lower altitudes, less in the Southern Ocean, and more in the Arctic region. Okay, so going back to what the main focus was, these two constraints. Our burden is a bit too small, so we're underestimated, but the mercury lifetime is actually within the constraints, which suggests that perhaps the lifetime should actually be longer since the burden is too small. And this big difference is a combination of both redox effects with removing the reduction and adding the additional oxidation. And so, as I said, we're overall biased low, but the seasonality looks fairly similar, as well as the spatial variability. And in addition, we seem to have an improvement in the Arctic seasonal cycle, likely because of the improved bromine representation in the Arctic. Okay, so what do we do about this underestimate? One thing that, I guess that's my cue to stop talking. But very quickly, something that Noel is going to be talking about later is that we assume a quasi-steady state for mercury Br, which is the intermediate. And so we might need to think about revisiting the way that we calculate mercury chemistry, allowing that to change, which would then lead to lower completion of oxidation because the rate that I'm including for mercury Br decomposition is actually much, much higher than the previous version. But with this quasi-steady state, we're sort of forcing it to go through to completion. So that might help. And perhaps there's a lot of new papers coming out about mercury reduction. So if we can find a real mechanism, that could also be revisited. But I'm looking forward to discussing more to get more ideas about what to do. So thank you very much.
We have time for a couple of questions. Noel.
So I have a question about the influence reduction. I was wondering if you could talk about how that interfaces with what emissions inventory you're using, because a lot of the different emissions inventories that we have as options have different assumptions.
Right, so I think this is definitely something that I will need to improve in my simulation, because right now I haven't changed the speciation. So I'm just using the base inventory with the base speciation and not applying the influme.
Newer UNEP or the older?
I think the older, yeah, I haven't changed it from V902. So that's definitely something that I should update, and I think that will also improve our bias as well.
Yeah. You motivated removing in-cloud reduction by the large amounts of Hg2 in the upper atmosphere and lower stratosphere. Have you evaluated the model against that?
So I've been trying to, using some Carabic data, but unfortunately the older data had some issues, especially going into the lower stratosphere. So I just got some newer data, so I'm hoping to focus on the vertical profile evaluation soon.
can look at how what the position of mercury changes with changes?
Yes. Yes. So one of the big differences is actually from the bromine field. So now we have a lot less deposition over the Southern Ocean because there's a lot less bromine there. But yeah, actually overall, the magnitude of total deposition is not that different because the overall burden of mercury zero is smaller, and the oxidation rate is a little bit slower in my version. But I can't remember other spatial features off the top of my head.
Last question.
So you added in this chlorine as an oxidant. First, how well constrained your chlorine fields, and second, did that have much of an impact to the other oxidant changes?
Yes, so it is not super important. It's that little pink slice right there. And the chlorine fields I'm using from GMI and from Johann's halogen geoschem work. So I haven't really looked at the comparisons of that to observations. But
Thank you.
thanks.
Noel? Noel Stellar is up next.
Thanks. So just continuing along some of the topics that Hannah introduced, I'm going to talk about some ways I'm thinking about constraining this mercury oxidation problem in a very different way using some of the observations from the NOMADS campaign. So again, as Hannah introduced, we have a little bit of a mercury oxidation puzzle. We think, and we're getting more confident, that mercury reacts with bromine in the atmosphere in a two-step oxidation with the intermediate HGBr, which then reacts with OH, bromine, and others that Hannah mentioned to get Hg2. But there's a lot of uncertainties in the rate constants, and there's also a lot of uncertainties in the ways these compounds are measured with traditional measurements. So it's really a challenge to constrain these oxidation processes, looking at geoschem in the context of data constraints. So I'm proposing sort of a new idea to look at this, and that is to look not necessarily at the concentrations of elemental mercury, reactive mercury, but to look at mercury oxidation ratio. So traditionally, ratios of hydrocarbons of different lifetimes have been used to measure the effective oxidation age of air. And so when we think about mercury, you can think about it in a relatively simple term. So I'm going to ask you to sort of consider a parcel of dry air in the free troposphere. And the reason I say dry is because I wanted to avoid even the question of aqueous oxidation. But if that's not even happening, then we don't even have to have a dry air parcel. Just one that's not touching the surface. And mercury is then oxidized into Hg2. And what you can then assume is that the total amount of mercury is relatively conserved in that air parcel, except for mixing, which is a problem also with the hydrocarbon ratios. But then you can look at the ratio of total mercury at time t, or elemental mercury to total mercury, as a reflection of how oxidized that air is. My hypothesis really is that this mercury oxidation ratio can be used to better understand chemistry, maybe eventually as a useful time clock. But if that oxidant is something like an OH, it should correlate with the traditional OH time clocks. If it's something like a halogen, it should correlate with the halogen time clocks. We did use this in recent paper in ACP, sort of not the same. We did reactive mercury over gaseous elemental mercury, but it's close enough, and showed that observations from the free troposphere were different from the standard model. Again, there were some problems with those observations of reactive mercury. So in NOMADS, we think we have a better sense of what the reactive mercury is, so we can use that to test hypotheses. First thing I did was, because in NOMADS, the mercury observations were at 5-minute scale, I wanted to make sure that even the traditional hydrocarbon ratios were going to work, because that's, a relatively long time scale. So I looked at hexane propane and ipentane propane. So a traditional plot, it follows the plot that's done for a bunch of different aircraft campaigns in Parrish et al. So it's sees the expected behavior as air oxidizes, those ratios get lower, and that correlates with concentration of propane. And, you know, that's not a fit line, that's just a line to visualize the kinetic slope, but it just gives you a sense that this is sort of the expected behavior on average. Then I plotted up the mercury oxidation ratios, and they really have no correlation with the OH ratios. I'm not showing that. What I am showing is the one that had the most correlation, which was sort of the halogen clocks. That's N-butane, I-butane, which is used in chlorine. And that had a decent R. You know, I haven't really screened the observations. I just wanted to get a sense of it. But so, okay, we've got some initial indication that mercury is looking like a halogen. You know, there might be some possibility of future analysis with alkenes. We don't have a lot from we only had one from the NOMADS campaign to look at bromine specifically. But what about in GS Chem? And this is where I get to a point where I'm starting to think about what the limitations of GS Chem are to do this kind of analysis. GS Chem doesn't do particularly well, either in the bromine chemistry or in my test case with OH oxidation chemistry at reproducing the mercury oxidation ratio. And so if it were just a matter of, you know, we didn't have enough oxidation, if it was just the speed of oxidation, I would expect that we would have a decent correlation with the ratio, but not necessarily the magnitude we were expecting. And this really doesn't give me that much confidence. And the thing that really puzzled me was neither simulation had any relationship with, from a full chemistry simulation, the ethane-propane ratio, which I would expect the OH chemistry to do. So there's a couple things that are puzzling me. One in particular is that we're not using the OH fields from the full chemistry simulation. And so we're using monthly means. And for that reason, I don't think we have necessarily the day-to-day, hour-to-hour behavior that we really need from the mercury simulation in order to look at this. The other thing is, as Hannah mentioned, the effective first order rate constant. And so looking at what the sensitivity is to concentration, so OH does appear in that bromine mechanism. And while you might expect that would actually correlate a little bit, even if it's weak, with oxidation. So I was testing that out and looking at how in the standard chemistry, we actually calculate effective rate constants, and just did a numerical experiment with an ODE solver. This is the ODE solver in MATLAB because it just seemed to be easier to do that for different OH, bromine, temperature, and pressure. And found a low bias relative to the calculated rates that are used in GS Chem. So again, looking forward to working with Hannah to see if this helps her problem. But I wanted to give a warning on people who are using the mercury simulation that we made a lot of assumptions early on that were really designed for global budget studies. And as we're increasingly looking at issues from aircraft campaigns of day-to-day measurements, we should really re-examine some of these assumptions. And that's it. I will take questions.
Are there any questions? Yes, Matt.
Well, I just came from a different mercury section, and the convergence of the discussion was on the errors in the measurements. And so I wonder if you comment on that with respect to your use of oxidation ratios.
So we're using the DOGS measurements, and for that, we're actually using the different, so Dan Jaffe measures total mercury and then measures elemental mercury and then calculates reactive mercury by difference. For the oxidation ratio, we're actually just using elemental mercury and total mercury. So I think it might potentially be a little bit more robust, and in particular in this data set, it's probably the one we trust the most. The noise in the elemental measurements themselves aren't. And we were looking at free tropospheric air, so it goes up. There are quite high concentrations of reactive mercury. Yeah, so it goes, I think the range was like to 0.6 in that ratio. And again, we weren't getting that in GS Chem, partly because we didn't have enough reactive mercury, but also because I don't think we're correlating well.
Any other questions? Danielle.
Do the time scales work out for your simple free tropospheric model? Because the time scale for oxidation of elemental to mercury 2 is pretty long. And so over those time scale, ignoring deposition, ignoring mixing, is this?
Well, we actually are finding from the NOMAS data, and part of the reason that this was inspired by that is that we're finding high levels in free tropospheric air that has had 5 to 10 days of oxidation time. So we were measuring some of that air, and again, I think we have some evidence that oxidation speed might be higher than we think it is. So if we see it, then even if it's small, we should be able to see that signal. And you do have some hydrocarbon ratios that are on intercontinental types of timescales. So I'm going to look at that and see whether it correlates with more long-lived hydrocarbons rather than shorter-lived. Again, I'm a little bit limited by the hydrocarbons that are that were measured, but also the ones that are available in GSChem.
Any other questions? Thank you. Next speaker is Xilang Wu of Michigan Tech.
Thanks. Hello, good morning, everyone. So today I'm going to show you some adventure we had with the GeoScale model. So this work is largely done by my former postdoc, Dr. Kaming Wei, and graduate student, Xueling Li. Thanks. So why do we care about this, and why do we care about this arsenic? So the short answer is that arsenic is toxic. So actually, it's very toxic. So historically, it's called the king of poisons. And obviously, in earlier days, so it was very hard to detect the arsenic poisoning. So it was popularly used to murder some prominent figures. So it's also called poison of kings. And obviously today, we don't have many kings, so they're concerned about this. However, so there are increasing concern about arsenic in the environment because it can cause various cancers and many health problems. So just in 2013, so the EU has set the standard for the national, the European standard for the ambient air of arsenic concentrations. And so that's annual mean at 6 nanogram per cubic meter. Currently, I believe that's the first standard in the world for the ambient air. And the US EPA does not have this standard. It only regulates drinking water, but things may change in the future. So because the fast increase in concern on this from the public. So one example is that, so just a couple of years ago, there's a study by Consumer Reports. They tested many rice and rice products in the US, including some even organic baby cereals. And you can see that many of these, so they show that quite high concentrations of arsenic, which was very, very surprising. Another example is that very recently, I think that probably just 1 month or 2 months ago, so there's a class action lawsuit against some California winemakers. So they found so that quite high arsenic in wines. And I think that is particularly concerning to me because I feel that I can live without the cereals, but probably I can't without wine. So where do these come from? So we wanted to find out so that how the arsenic is getting transported, deposited in the different regions. So there are both anthropogenic and natural source for arsenic. So for the present day, the anthropogenic one is dominant. So especially for metal smelting, coal combustion, these are two most important ones. With some other contributions, relatively minor. So, and then for the natural source, the most important one is from volcanoes. Okay. So in this work, we tried to put in GeoSchem this source from the most important ones, okay, from coal combustion, metal smelting, and volcanoes. And so for some of these, for some regions, we have this regional emission inventory available. For example, the US, EU, Canada, Australia, Chile, we get this, we put this in GeoScam. But there are some regions we don't have such information. So for example, for China, we had to develop the inventory from scratch. So basically we get the production for metal each year, and then how much coal is being used. So we put in this, we apply the emission factor for these various sources. And so we derive the arsenic emissions. And then there's there's still some parts we couldn't even get such information like a coal combustion. So we apply this, the ratio between arsenic and sulfur based on the SO2 inventory. Okay. So this, after we put into the major part, a major challenge and major effort was to develop this inventory. So after we put in this together, we put in the GeoScale model, we run the model for a full year, and at the resolution 4x5. So this is what we get. So that basically the background shows the model simulated annual mean concentrations of arsenic, total arsenic. And then those circles represent the observations. Okay, so at different sites, we have totally about 20 sites around the world. Probably for some of them, it's hard to see here, but which that just simply means the model has been working too good. So that agreement, very good agreement. So you can hardly see some of them. However, we do see some underestimate for like over China. Okay, so that you can see that. So, and we think this is most likely due to the emission factors. So those we get the emission factors from literature, which is based on studies in the US, in Europe, and in China. So the emission factors could be higher than that. And then we carried out some sensitivity tests to look at the source receptor relationships for various regions. And for example, the first one is showing the contribution from Asia, from emissions. And you can see that it's getting transported from Asia to across the Pacific and all the way through North America. And then this, the lower one shows the contribution from North American emissions. And to summarize this, quickly summarize this, so this is the table. Basically, we can see that if we look at the receptor, we look at the receptor regions, okay? So listed here, and so this is the different source regions. So for example, if we look at North America, so the first one is showing this is the concentration, how much of the arsenic in the air is attributed to Asia emissions. And this is the deposition. So if we look at the deposition, it's about 1/3 is attributable to Asian emissions. Okay. And so obviously this number is higher for the Western US than the Eastern US. Okay. And I think that's all. And so that's basically the take-home message is that so we have developed a module in the GeoScale model, which can allow us to simulate the global transport of arsenic. And so this model has worked very well, actually surprisingly well, so that to simulate the total arsenic concentration and deposition around the world. And I think that's all. I would like to take questions if you have any.
Questions? Yes. Yeah, very interesting part. Any active chemistry involving arsenic in the atmosphere?
No, not at this point. So basically, what I'm showing here is just the total arsenic. We haven't been that far yet to resolve the different species.
So there is some chemistry
There,
included.
that's right. So that's right. Yeah. But the effect on the total arsenic probably is relatively small. It could affect the water deposition. So because different compounds would have different solubility.
So final sources, you have wood preservation. What do you mean with wood preservation?
Can you repeat that again?
Yeah, in your slide of the sources of percentage,
Mm-hmm.
wood preservation in the anthropogenic sources.
Right, because historically people had been using arsenic for wood treatment so that it will stay longer. It's still being used today, but it's relatively a smaller contribution to the total source. Yeah.
You mentioned that you thought emission factors might be linked to the underestimate over China and South America. Could it possibly the monitors themselves not representative of such a coarse simulation? Did you investigate at all what the difference in resolution might be?
Well, I think that the resolution may not be a major issue here because for the other regions it works as I've shown very well.
I'm thinking of Chile, for example, a lot of the mining is in the mountains. The mountains have obviously lots of high resolution features in favor of monitors that might actually produce a bias which might be correct in terms of the 400 by 500 kilometer area. But the only sense that the local observations or they represent the broader area.
Yeah, so that that could, but so that on the other hand, that so the emission factor does still sound a more reasonable one because, as I mentioned, so all the previous studies on this were based on this the numbers from the U.S., Europe, and we know that so the control technologies generally so that has working better so in the U.S. and. So, and also that the overestimate, the underestimate, it's not that much, 20%, 30% about it. So that's, but that's, a good thing to check on.
Yeah, just following up on that, I'm guessing that many of the places that you don't have observations are also where you don't have good emissions. And I was wondering if you thought of doing a sensitivity simulation where you use the emission factors locally and see how much that changes things over like the US and Europe where you do have good emissions and you could constrain that emission factor maybe a little bit better.
Yeah, that's good point. Maybe we should check that. If that's not working, we can go back to this. Yeah.
Thank you. Next speaker is Carrie Friedman from MIT.
Thanks. So I'm going to be switching from metals to organics and talking about a model I've been developing, a PCB model, and show you some initial results from that model. So I thought I'd talk first about why you should care about PCBs, and it's basically the same story that we've heard from mercury. PCBs are toxic. They persist in the environment. They have a structure that makes them really resistant to degradation. They can transport long ranges in the atmosphere through this effect called the global distillation, where they're emitted at the warmer latitudes and then they condense and deposit at colder latitudes. And they also bioaccumulate, especially in the marine food web. So this is enough to be concerned if you live in Cambridge, but you should really be concerned if you live in the Arctic and you follow a traditional diet because you're exposed in a multitude of ways at high concentrations. So because of this, we have a project that is going to look at the influence of emissions, the chemical properties and the biogeochemical processes of PCBs and their effects on the transport and fate of PCBs to the Arctic in particular. And we're working on the atmospheric component, and Elsie Sunderland's group with Helen Amos is working on an ocean model for PCBs, which we hope to couple and look at the combined impacts of atmospheric and oceanic transport on PCBs in the Arctic. So the PCB model is basically just an expansion of the PAH model, which it's been a long time since anyone has heard about the PAH model, so I thought I'd just review it here. PAHs are emitted to the atmosphere, and then they can partition between 3 different phases, the gas phase and 2 different particulate phases, a black carbon bound and an organic carbon bound. And the particulate phase can be oxidized by ozone, the gas phase is oxidized by hydroxyl radical, and all 3 phases can dry and wet deposit. We've been able to use this model, by the way, for 4 different studies successfully. So it's fairly well established. The PCB model has been modified from the pH model in a couple of different ways. So there's really no evidence of oxidation of the particle-bound phase by ozone, so we've removed that. Also, there's no evidence of preferential binding to black carbon for PCBs the way there is for PAHs, so we just consider a combined particulate phase that partitions from the gas phase following a single partition coefficient. And we've also expanded from the atmosphere to look at 5 different surface components, so ocean, soils, vegetation, lakes, and a snow or ice component. And eventually, as I said, this will be replaced by a full ocean model. It's very simplistic at the moment. Each of these different surface types can have losses of various types depending on what you're looking at, and they can also re-emit to the atmosphere, which is why we have them, because PCBs persist for so long and they can last and re-emit. So there are 209 different PCB congeners because of the different ways that you can chlorinate these 2 phenyl rings. For our project, we're looking at 7 that have been deemed important by the International Council for the Exploration of the Sea. And just for this presentation, I'm just going to show you results of PCB 28, which is trichlorinated, and PCB 153, which has 6 chlorines. So just some initial evaluation results. I looked to a previous publication that evaluated one of the more widely used and known POP models called Better Global. And so their standard for evaluating their model was to look at what % of the simulated concentrations fell within a factor of 10 to the 1/2 and what % fell within a factor of 10. And so at 15 by 15 spatial resolution and driven by a GCM output, they found that 64% were within a factor of 10 to the 1/2 and 96% within a factor of 10. And then GeoSchem, where we're running at 4 by 5 and obviously driven by reanalysis data, we find that we have 77% within a factor of 10 to 1/2 and 98% within a factor of 10, so that's promising. And then just some initial annual budget results. So I'm showing first PCB 28, the global budget, and this is kind of a busy slide, but I want to highlight some main things. PCB 28 exists mostly as a gas, so you have very small concentrations in the particle phase. And the major losses are by oxidation. That's really the biggest loss for PCB 28, and through dry deposition. Ocean and soils are not at steady state, whereas the atmosphere, vegetation, lakes, and snow or ice are. The ocean and soils are losing more than they are taking in, so they're actually re-emitting legacy deposition. And now I'm just going to compare and contrast PCB 28 to PCB 153, and I'll start with the atmosphere, and then I'll move to different surface components. So the atmosphere is at steady state for 153 as well. There's a greater particulate fraction for PCB 153, so if you see the gas phase, there's a smaller concentration overall, but more of it is in the particulate phase. But actually for both, it's still very small. It's only less than 1%, which is different from pHs, which can have, depending on the pH, almost 100% in the particulate phase. Major loss route switch between PCB 28 and 153, so for 28, it's oxidation, but for 153, dry deposition is the major loss. If you look in the surface components, the big thing that I want to point out here is that even though PCB 153 has had 5 times fewer emissions over time than PCB 28, you have higher concentrations in the soil and just proportionally higher concentrations in most surface media. And that's just because it's more persistent. So the more highly chlorinated PCBs are, the greater they're sequestered, the more persistent they are, and the lower their secondary emissions back to the atmosphere. So that means less secondary long-range transport. So we're planning to look at the Arctic, so I just wanted to show some initial results from the Arctic. This is measured PCB 28 versus modeled at Zeppelin. And you can see that I'm having some issues here where the seasonal cycle is opposite what's observed. So basically, wherever you see a peak for the measured seasonal cycle, you see a trough for the modeled seasonal cycle. If you look at a mid-latitude station, this one comes from the Great Lakes, from Environment Canada, we're actually doing pretty good capturing the seasonal cycle. So I'm trying to figure out what's happening here before we go on to look in detail at the Arctic. And this is just another way of looking at this. I've averaged over that time series that I just showed you to show that indeed on average the model is saying we should be lowest in the summer, whereas the measurements are saying we have the highest in the summer in the Arctic, but we're doing okay in the Great Lakes. So that's all I had. I just want to thank the following people and funding agencies and take any questions.
Are there any questions?
Hi, Elsie. That was an idea, and I've tested the ocean in this model, and it doesn't make a difference. It basically just kind of lowers the concentrations. I thought it might be snow cover, so there's some debate as to whether snow is actually hindering re-emission, and once the snow goes away, the ocean's going to re-emit all this PCB. Also, when the snow melts, it's going to release all this PCB. And but you know, if you actually look at the way snow re-emissions are parameterized, snow is basically just kind of like air. So it just kind of recycles and actually buffers the atmosphere. So I tested that as well, and it didn't really just kind of raised or lowered, didn't change the seasonal cycle. So my next thought is oxidation, and whether we have the oxidation rate constants that we use are maybe a little bit too strong, and it's getting rid of some of what's in the Arctic, but not really touching anything near emissions.
Any more questions? Yes, Chris.
From your global budget, it looked like the lifetime for both was about just a day or two.
Yeah.
But then the concentrations at Zeppelin were order of magnitude comparable to those at Great Lakes. So how is that?
Yeah, so that's kind of what I'm wondering too. I think just from re-emitting, so this is the hypothesis with these is that they grass hop. So they're emitted, they deposit, they're emitted, they deposit, and they continue to do that until they reached cold latitudes. So, you know, I'd have to figure out a way to test that explicitly, but I think that's what's going on because you see that much more for 28 in the lower chlorinated congeners than for 153. The Arctic concentrations are pretty low compared to the mid-latitudes.
Do you have much constraint on what's in the soils, especially in the Arctic? And could you make it could part of your seasonal problem be from re-emission from soils that are frozen and thawing out in the summer and allowing that re-emission?
It could be. I've actually done a sensitivity test where I've just turned off all secondary emissions. Doesn't really make a difference in the seasonal cycle, but we don't have good constraints on soil concentrations, especially in the Arctic. We're starting to get some. We're actually working on a second project with Michigan Tech where they're doing a detailed analysis of concentrations in surface media, which will help. But so far in the model, I don't think it's the secondary emissions that's causing that.
Thank you.
Yeah.
Next speaker is Viral Shah, University of Washington.
Hi, good morning, everyone. I'm Viral Shah, a graduate student working with Liat Jigli at the University of Washington. And I'll be continuing this discussion we have been having about mercury oxidation and focusing on NOMADS observations and have my take on the NOMADS observations. Okay, so just a little detail about the NOMADS campaign. It was held in June and July of 2013. Speciated mercury measurements were made by Dan Jaffe's research group over the southeast US. I used the GeoSchem mercury model to interpret these observations. We used the quarter-degree nested grid model over North America with a couple of updates. One is to the emission inventories, and the other to the chemical mechanism, which is very similar to what Hannah proposed earlier in the day. So I'll be showing results from this simulation as well as two sensitivity simulations. So first, how do these how does our model compare with the observations? On the right, I have total mercury, and we see that in the mean concentrations of total mercury as well as the vertical profile, the model does very well compared to the observations. This tells me that the emissions and the lifetime and the representation of these processes, at least over this region, is good in the model. For oxidized mercury, and as Noel said earlier, model is biased low by a factor of about 3. And we can see the systematic bias in the scatter plot here with about 18% of the observations or with 18% of the model values within a factor of 2 of the observations. So we think this is because the oxidation rate in the model is a bit too slow. So the 2 factors governing the oxidation rate in the model are bromine concentrations and the oxidation rate constant itself. With bromine concentrations in the current version 902 are based on Justin Parella et al.'s implementation of bromine chemistry in GeoChem, and a figure from their paper shows that there is an underestimate in BR concentrations in the tropics and the mid-latitudes. Well, I'm very encouraged to see Johan's work that has bridged this gap considerably. But for now, I compensate for this by increasing the bromine in the troposphere by a factor of 3. On the other hand, we have the rate constant itself, and there's a factor of 5 to 10 uncertainty in the rate constant. In GeoChem, we are using the lowest of this estimate. I run another sensitivity simulation with the largest of this estimate. So with the sensitivity simulations, we see that total mercury, the model performs well with total mercury in all 3 simulations. There is a marked increase in improvement in the model simulation for oxidized mercury, especially above altitudes of 3 to 4 kilometers. We see this improvement in the scatter plot, and about 30 to 50% of the model values are now within a factor of 2 of the observations. I think this indicates that the oxidation of mercury in troposphere is about 3 to 5 times faster than what's currently in the model. Many of these points, measurements, were taken during flights over Texas, and I'm going to show one flight in more detail. This flight was RF6 over Texas, and we saw very high concentrations of oxidized mercury at about 6 to 7 kilometers. We saw concentrations of about 300 picogram per meter cube. We also see that the standard model, or the base case simulation, gets an enhancement in this region, which gives me some confidence in the oxidation mechanism that is in the model. We can see the magnitude is well simulated by the FAST-K or the 3 times BR simulations. We run the NOAA high-split back trajectory model for this air mass and find that this air mass spent 3 or 4 days in the Pacific anticyclone, subsiding from an altitude of 10 to 12 kilometers before it was transported over to Texas. It seems to be a fairly regular occurrence of this pattern of transport, and GeoChem seems to be getting the timing of this transport right too, as we see in this flight as well as 2 other flights over Texas. Now, at the 500 hectopascal level, what we see is hotspots of oxidized mercury in the subtropical anticyclones. This is the summer of Northern Hemisphere. And whenever during NOMADS, whenever we measured high concentrations of oxidized mercury, we could trace back that air mass to one of these anticyclones. So what's special about this, what we hypothesize is that oxidized mercury is produced rapidly in the upper troposphere. And in these anticyclones, it subsides down to lower to 500 for 400 hectopascals. And these anticyclones are characterized by dry air mass. So there isn't a deposition due to scavenging or decrease in oxidized mercury due to reduction. So these are reservoirs of oxidized mercury, and oxidized mercury from these areas can be transported over to North America or other regions of the world. So to conclude, we find that the GeoSChem model does well in simulating total mercury concentrations observed during nomads. For oxidized mercury concentrations, the base simulation is a factor of 3 too low, but the simulation improves with higher bromine concentrations or a higher oxidation rate constant. We find that the subtropical anticyclones are reservoirs of oxidized mercury, and one possible implication of the faster oxidation is, in my view, faster reduction, and that goes against what Hannah was proposing earlier, but that's something we can discuss further. And I say this because the lifetime of total mercury is fairly constant, fairly constrained, as we saw from the observations. And if there's faster oxidation, I think there is a faster reduction to balance that faster oxidation. Thank you.
We have time for a couple of questions.
So in your scat bar, something shows up that show up in Noel's plots too, that there seem to be two wings really. One in which the variability is relatively similar to the observations, though not great, and then this other wing where mercury 2 is very low across a range of observed, across the range of observations. What is that? What is that other? Or it shows up in those plots too.
Right. Okay. So these observations here were made particularly on one flight over the Atlantic Ocean, and well, the GeoSChem doesn't do very well in capturing that enhancement, especially with even with the 3 times bromine or the fast K simulations that I showed here. We could capture some of this enhancement when we increase the oxidation rate even further, and so that's one. And the second reason we see is that the GeoSChem doesn't get the transport of that air mass correct as well. So this was a pocket of very high oxidized mercury which we measured through, and that pocket was misplaced slightly in the model. If you had anything else to add, Noel, to that?
Yeah, that's where I think the potential for look at the hydrocarbons, because if we get that air mass in the hydrocarbons, then we've got some problem with mercury.
Danielle?
I don't understand why total mercury is so buffered against changes in the oxidation rate constant.
Well, so the total mercury in these scenarios I've constrained using the reduction rate. So the oxidation increases, but since we have a very well-defined total mercury profile, I constrain it with the reduction. So the sensitivity simulation look only at oxidation and reduction and not changes in total mercury, which is a whole another game.
Oxidation, you correspondingly increase or reduction.
Well, that's right.
Thank you. Next speaker is Wanship Yang.
Hello, everybody. My name is Huan Jin, and I'm currently a PhD student from Michigan Tech. So today I'm going to talk about my work to study the effects of changes in climate, and then cover on atmospheric mercury. So why do we care about mercury? So a lot of people have talked about it. Mercury is toxic, and also mercury could bioaccumulate in aquatic system to form methylmercury, which could have effects on human health, especially for those like Native Americans whose diet depend on fish, and some vulnerable people like a pregnant woman and the children. Also, elementary mercury has a longer lifetime, like on the order of a year. It could go through long-range transport, like for some remote areas like Arctic could suffer from this effect. So a lot of previous work has some previous work has done to study the changes in anthropogenic mercury emission on the mercury basin, but little has been done and little is known about the effects from changes in climate and then use and land cover, which is the focus of this study. So we used the GEOSCAM coupled atmosphere, land, and ocean mercury model, the Worden V902 at a 4x5 degree resolution. So to study the effects from changes in climate, we used the archive meteorology from the GACE GCM3 output, and following the IPCC A1B scenario to study the effects from changes of natural vegetation, which we refer to as land cover. We use the output from our PJ vegetation model, which is also driven by the GACE GCM3 meteorology data. And also we include the effects from changes in anthropogenic land use, mainly like the agricultural land use from the output from image modeling, also following IPCC A1B scenario. So it's a lot of coupling here. So we did a suite of sensitivity model simulations to separate the effects from changes in climate and then use and then cover. So first we look at the effects on mercury dry deposition. So this plot, this is the present day elementary mercury dry deposition velocity, and at the bottom two is the ratio of this elementary mercury dry deposition velocity change due to land cover itself and the combined effects from land cover and then use change. So we see from these two plots like a general increase in elementary mercury dry deposition velocity over most of the continental plates. By some places, like by a factor of 2. This is mainly due to the increase in leaf area index. As some previous talk, we see like the increase in leaf area index could affect ozone dry deposition velocity, which should be similar thing. And as a result, we see a general increase in elementary mercury dry deposition flux change, as you can see from the bottom two plots, by like 10 to 50%, which very correlated well with the change in elementary mercury dry deposition velocity change. While the effects from climate change could also cause the increase in elementary mercury flux, but it's more like a uniform change. It's not like a localized as effects from the vegetation change. Next, we look at the effects on white deposition, mercury white deposition flux change. So this is the present day white deposition flux, and this is the ratio of the total precipitation change, the ratio due to climate change. And thus bottom right is the ratio of mercury white deposition flux change due to climate change. So as we can see, the change in precipitation plays a very important role in the change of distribution of mercury white deposition flux change, which is expected to show the role of precipitation change. Look, the next one, we look at the effects on mercury gross deposition flux change. So the gross deposition flux is the sum total of white and the dry deposition. This is the present day gross deposition flux change, and this one is the ratio due to climate change, excuse me. And this bottom two plots is due to the land cover change. As first we look at the effects from climate change, it's the pattern is similar to the change in total white deposition flux. So it's the role of white deposition flux on the gross deposition flux change. And as in some places, like the high latitude, it could increase by up to 40%. But if you look at the change due to land cover and the use change, it's more the pattern looks at the change in mercury dry deposition. And also in some like changes, we could see a 40% increase as well. So next, to sum up, we look at the effects on global mercury budget. So this top part is the mercury source in the atmosphere, the bottom is the sinks. So first we look at the effects due to the land cover land use and the chains. We see the main effects of land cover land use on the mercury budget. It's through the changes in dry deposition, mainly elementary mercury dry deposition. And if we look at the effects due to climate change, we could see first climate change could affect the secondary emission of mercury, and also climate change could affect dry deposition process. And also climate change could affect mercury chemistry in the atmosphere and therefore affecting the mercury burden. So with that, I want to thank the funding agency, NSF, and my advisor, and a lot of mercury modelers in GeoSCAM who have helped me. So I would like to take any question. Thank you. Yeah.
Did you use the global terrestrial mercury model?
You mean the GTM map? No, I just used the simple, the simple one, the standard one.
So your changes are pretty small compared to the uncertainties that we've talked about in the global budget. How do you think about that question?
Yeah, I thought about that actually. Yeah, because there's uncertainties in the mercury chemistry, like the mercury model itself, and the uncertainty in the meteorology, like all the vegetation we use. But it's more like seeing, I think from my understanding, it's more like to see the mercury budget, the cycle, the different process, how robust and how different perspective response to the changes in climate or then cover that you change, how sensitive they could be, I think, comparing the different one relatively, I think that's a better way. Yeah, I don't know how to better quantify the uncertainties though.
So I noticed in your table that the source from biomass burning was constant.
Yeah.
I'm just curious, how well constrained is our understanding of mercury?
Oh yeah, that's a good question. So in my study, I just keep the same, but then the cover change could may potentially affect about what mass burning as well, which somebody else studied from my group. But in GeoSCAM currently, in the model I use here, the biomass burning, it depends on the carbon monoxide emission. So it's not really well constrained. So definitely more work need to be done there.
Thank you.
Thanks.
Next speaker is Xiaoqi San.
Good morning, everyone. So I will talk about my research on improving the parameterization of land surface exchange in the GeoSCAM mercury model. Okay, as we can see from the global mercury budget, that nearly all of the mercury is emitted from the surface in the form of Hg0 into the atmosphere. And this atmospheric surface exchange of Hg0 is very important to the global mercury cycle because it drives the mercury cycle. And if we don't have any mercury emission from the surface, we don't need to care about the chemistry we mentioned earlier. And our previous study, which has been published in NCPD, uses a top-down approach to constrain the global mercury emission and parameterizations in the GeoSCAM mercury model. We collect ground-based observations of Hg0, and GeoSCAM model is used to calculate sensitivities of the emissions and parameters to the observations. Using a Bayesian invariant approach, that we conduct two invariant cases. One is the emission invariant, and the other is parameter invariant. For the emission invariant, we optimize monthly soil and ocean emissions. For the parameter invariant, we optimize one soil emission factor and two ocean parameters. As we can see in the middle panel, both invariant cases improves the agreement with observations in North America and Southern Hemisphere. And the right panel shows the modeled ocean and soil emission fluxes, and we can see both invariant cases change the seasonal cycle of ocean emissions, and both invariants also suggest lower soil emissions. JuiceCam uses a two-layer ocean model, the mixed layer and the subsurface. The parameter inversion optimizes two ocean parameters, the dark oscillation rate of aqueous H0 and aqueous H2 HGP partitioning ratio. We also update several other parameters based on the recent studies. Our parameter inversion results agree with the field study and the lab study, which shows the dark oscillation of H0 in the surface ocean is highly underestimated. Okay, we further study the atmosphere surface exchange of H0 in the eastern US and northwest Atlantic by integrating measurement information from three types of observations. One is an aircraft campaign, the NOMAD has been mentioned in earlier talks. And we also compile ground-based observations of H0 from the US Atmospheric Mercury Network. We have 11 sites. And we also include 3 ship cruise measurements during the summertime in recent years. For the NOMAD campaign, we select background H0 data in the PBL. And we also divide these observations in 2 categories, over land and over ocean. And we will see the results later. We conduct several JuiceCam latitude-grade simulations over North America, including the reference simulation, the version 902, and the parameter inversion and sensitivity simulations. The sensitivity simulation number 1 is the same with the parameter inversion with 2 differences. One is elevated springtime soil emission in the mid-latitude, and the other is the summertime warming columns in tropics and subtropics. The increase of warming columns in the tropics has mentioned by Viral in earlier talk. This is to reproducing the observed very high H2 concentrations during NOMAD. And we found that an increase of springtime soil emission is consistent with results with the emission inversion as shown in the left figure. 2 factors may contribute to such increase. One is agricultural activity in the springtime, and the other is because we have a larger land surface mercury pool due to deposition in the snow in the winter time. Some of the previous mercury zero exchange flux measurements support our hypothesis of increased springtime soil emission. And I will then show some model observation comparison results. The left figure shows ammonite H0 concentrations. Among different simulations, we found that sensitivity simulation can best capture the seasonal cycle of observed ammonite H0 concentration. During the NOMAD period in 2013, June and July, the sensitivity simulation only have a very small bias when compared to the ammonite, the overall ammonite measurements. When we comparing our simulation with ship cruise aqueous mercury concentrations, we found that the sensitivity simulation also gives closest aqueous H0 concentration among different simulations, but still 8 to 40% lower than the ship cruise measurements when, in terms of H0, aqueous H0. Therefore, we made another sensitivity simulation by increasing the ocean emission of H0 in the northwest Atlantic by 80%. 40% is for the decrease for the underestimation of aqueous H0, and we know from the previous studies that the parameterizations of atmospheric surface exchange may lead to 30% atmospheric ocean change may lead to 30% uncertainty. So this 80% represents an upper limit of ocean emissions. And we can see from the right figure, this is the back trajectories of the ocean measurements during NOMAD campaign. And we see most air masses are the air mass usually has been several days in the ocean when being sampled. And we found the H0 concentration from NOMAD is 1.64 or 1.46 nanogram per cubic meters, which is about 10% higher than our model simulation. The overall uncertainty given by the NOMAD measurement is about 10%, and so we see there's a bias. We see there's some bias here. And as the last, I will show the comparison with the NOMAD concentration. We see the sensitivity simulation is better than other simulations, but can still not produce the very high H0 concentration observed from the ocean. So, take-home message. GISCAM simulations and observations suggest that the eastern US land is a net sink of H0, while the Atlantic Ocean is a net source. Okay, thank you. I will take any questions. Hi. Yeah. Yes, yeah, I show 3 mercury species: the air Hg0, the aqueous Hg2, and aqueous Hg0 and aqueous total mercury. So you can see we are little underestimate. We have a little underestimation of the atmosphere H0 concentration, but still within uncertainty from the ship crews. Yes, I mean, if we see this the table. Okay, sorry. I mean, from the reference simulation to the parameter invariant, because we changed the 2 ocean parameters, so we can model higher aqueous H0 concentrations in the surface ocean. But even after we changing the ocean parameter, we still have a underestimation of aqueous H0 concentration in the North Atlantic. So we increase the ocean emission of H0 further to comply with our ship cruise measurements. So I mean, so that's why I say that this 80% increase represents the higher limits given by the ship cruise measurements. Hi, Jenny?
Yeah, on the soil emissions, you said you increased them probably because of the agricultural source and maybe the snow. Did you do that based, like, was that just an across the board increase the soil everywhere, or did you do it based on patterns of agricultural use?
I haven't done that. What I'm doing now is that I increase the soil emissions in the mid-latitude region overall.
The last platform speaker this morning, Yanshu Zhang of Harvard.
Okay, good morning, everyone. My name is Yanshu Zhang, and I'm a postdoc at Harvard working with Daniel and Elsie. So today I will talk about the atmospheric mercury trend and try to give a new explanation of that. So since the mid-1990s, we have observed mercury concentration in the atmosphere has decreasing in many regions. So here I show a quick summary. So we found the mercury concentration decreasing in Caminite over North America, and also in Macy Head, which is near Europe here. And even in the South Hemisphere, we also found some decreasing trend too. So we found, for example, for the Macy Head, which has the longest and most robust observation over there, we found that mercury concentration has decreased around 20% in the past 15 years. So this is kind of against our expectation. If we look at the global anthropogenic mercury emission, so actually it's increasing. So this apparently become a conundrum for the mercury community we have scratched our heads for a long time. So one of our past study in our group has given hypothesis. So we are thinking that probably this associated with ocean emission decrease. So because we found the seawater mercury concentrations in the North Atlantic Ocean in the past 10 years, 20 years, it will decrease very fast. So because the mercury from the ocean can also evasion to the atmosphere, so this decreasing mercury concentration in the ocean could also drive a mercury trend in the atmosphere. So from this study, we found that we can explain a lot of the observed trend. However, later we realized that this really high concentrations in the 1980s something is probably highly possible to contaminate samples. So it make it less trustable. So that means this hypothesis probably is problematic. So today I will talk about kind of an alternative hypothesis for that. Is that only associated with regional emissions? So let me give you some clue over here. So if you look better again about what we have for the observed trend, basically the most of the trend that we found is happening in North America and Europe. If you look at the regional emissions, a much clearer clue we can get from that too. So if you see the regional emissions from North America and Europe, and even in the former Soviet Union, we see the mercury emissions decreased a lot. Actually, the global emission increasing in the past 20 years is actually only driven by Asia. So this gives our clue that probably the mercury trend in atmosphere decreasing over there in these regions is only associated with the regional emissions. On top of that, one another study in our group gave new emission estimation for largely uncounted sources, basically from a consumer product consumption. Here are some examples such as lamps, batteries, paintings, etc. So in this study, we found that the mercury emission from these pathways actually is very significant. In the 1990s, it's about maybe half of the previous given numbers. And furthermore, we found this uncounted emission source in the developed countries actually is decreasing very fast in the past 30 years by an order of magnitude. So this also can reinforce our hypothesis of the regional emission trend are driving the regional atmosphere trend. So on top of these two emission inventories, we also updated some other emissions, such as emissions in China, which is actually a new estimate as showing that it's much flat than previous thought, and also updated the Indian emissions, emissions from artisanal small-scale gold emission, and etc. So with all these emissions together, we found our new emission actually suggests a decreasing trend for the total mercury emissions in the past 20 years. So we put these emissions into Josephson model, try to give a hypothesis test against a lot of observations, at least here. So here shows the result. So first thing I want to introduce is a Carabec project over here, as shown in the green dotted line. So this is observations in a free troposphere because of a larger footprint. So this is actually more representative for global background emission. So we see the trend is much weaker than the observations over the ground surface, which is a very strong regional signature, as shown, as I can see in this figure here. So this gives us some confidence that the mercury emission, the atmospheric trend is probably just driven by regional. However, in the free troposphere, the global background emission trend is much flatter. So here we also give some statistics for the ground surface. So we see for the cabinet and the EMA and PSATs, we generally capture the magnitude of the trend. And here I pay special attention to the Macy head, which is we believe is the kind of best trend study over there. We found the model can very well explain the trend, probably associated with North American and European emission decreases. So here we also look at the mercury 2 deposition. So we say this carries an even stronger regional signal because of the much shorter lifetime than elemental mercury. Again, we also compare with observations over EMA and PSATs. and MND network over United States. Both of them are showing the trend. So we found not only the average magnitude, but also the spatial patterns the model actually captures very well. So at the last 1 minute, I will pay special attention to the United States trend, because in 2011, the Obama administration has proposed the world first emission standard for power plant emissions. So in that emissions, they will require the power plants to require some mercury-specific techniques to reduce their emission. However, very recently, this rule is challenged by industrial groups by arguing that this rule requires billions of dollars of cost to install these techniques, but the benefit is only $1 billion, something like that, to associated with the decreasing mercury depositions. So this motivates us to look at what drives the mercury emission decrease in the United States, especially over the past 5 or 7 years. So we found that the mercury emission decrease from power plants over there is largely associated with the co-benefits of installing SO2 techniques. We found that in terms of mercury 0, mercury 2, here we attributed the reasons for that. We found the mercury 2 emission reduction is largely associated with SO2 control, as we show here, whereas for mercury 0 is largely associated with NOx emission control. So this gives a very interesting implication. So that's connects the mercury emission with SO2 emission. So if we look at the global SO2 emission trend, we found that globally it's decreasing. And very interesting, we found China is also decreasing, especially from power plants over here. So that's why the Chinese mercury emissions is also kind of become flat these years. Interestingly, India doesn't pick up this trend yet. We found that the SO2 emissions continue increasing. So that means that the Indian emissions for mercury is increasing much faster than China. So the last, I want to talk a little bit about the policy implication of my study. So first thing we found that in the developed countries, the emissions from consumer products has played a very important role for our past trend. So we should keep doing this in developing countries, which is very important to reduce the mercury level in the atmosphere. The secondly, we found the mercury emission could benefit from installation of other control other substances such as SO2. So if especially for the Indian, if the installing mercury specific technique is too expensive, just put on some SO2 emission control technologies. It works for mercury too. So, but this is probably not the case in developed countries because they have already installed very much high potential of these SO2 control technologies. So for these countries, the mercury specific technologies is required. Yeah, that's it. Thank you very much. Happy to take any questions.
Are there any questions? Well,
yeah, you make the argument that the trend can be explained by regional emissions. How sensitive is that to our understanding of what the lifetime of mercury is? I would imagine that it's pretty sensitive, and we've talked about uncertainties in that.
Yeah, yeah, that's a very, very important one because we say the lifetime actually is links the emission and the concentration. So we found here, I think here our result is quite robust because we say the emission trend, which is unconscious previously, especially from mercury for commercial products, actually that's very large. So that makes the global mercury emission trend actually now is decreasing. So which is a very strong argument that even the atmospheric mercury lifetime is changing a little bit, but it will not change the trend very much over there. I mean, the decreasing trend is always there.
Thank you. Now I'd like to ask the poster presenters to queue up for the brief poster introduction.
Hello. So I'm going to introduce my poster, which is a parametric uncertainty analysis with GSChem. And although it's an application to pH simulations, I think it answers a question that everyone should be interested in, which is how does uncertainty in the input parameters like constants and rates and things like that translate into outputs? And in my work, I use a response surface model, which is basically a simplified representation of how the model responds to inputs, and I'm out of time. So come see poster C1.
Hi everyone, I'm Aditya Kumar and I'll be talking about the impacts of future land cover change on mercury biomass burning emissions. So we are combining literature estimates of mercury emission factors and available biomass together with the land cover dependent scheme of combustion efficiencies and fire output for fire frequencies, land cover output from the LPGA land cover model, and burned area output for a statistical model to estimate the emissions for present and future. Our emissions show a 50% increase in the future along with the global distributions for present and future as shown here, and the differences and percentage differences. I would be happy to share the details in the post session. Thank you.
In this work, we think about what the recent United Nations Minamata Convention for Mercury might mean for coal-fired power plants in India and China, queued up well by Yingxu's talk. So we use interviews with convention negotiators and document analysis to identify technologies that could be consistent with convention. We translate these technology choices into emissions estimates, and then we use geochem to evaluate impacts on deposition. So if you're interested in interactions between energy, air quality, and mercury policy, and how we can use geochem to evaluate these interactions, come to my poster.
Well, as you can see, geochem does not reproduce very well mercury concentrations in Antarctica. This is mainly due to the fact that we don't fully understand mercury reactivity in polar regions. But based on the 2-year record of mercury concentrations, we now have new insights into mercury reactivity in central Antarctica. So if you're interested, come to poster number 4.
Good morning. My name is Aurélien Domer. We come from Grenoble, Hélène and I. Yes, we saw that global model doesn't really reproduce trends and seasonal patterns in the southern hemisphere. So, one of the reasons why is that there is a lack of measurement in those regions. So we launched 3 years ago in the frame of GMOS program, Global Mercury Observation System, continuous measurements in the southern hemisphere. So you will see on the poster 3 sites. One is Amsterdam Island, mid-latitude, and 2 of the sites in Antarctica. And so if you are interested in those measurements, please come and see the posters. And also we are hiring people to work in this region. So also we have position to offer. Thank you.
Thank you all. This concludes the first morning session. And we will reconvene at 10:10 for the second morning session.
Yes, it was
Well, we believe that's
This is the only one, yes.
Forest. I used average, not absolute. Hey, at least I caught it. I don't want to be on a bingo board. It's not really blatant, but there is a difference.
Same name?
Yeah. What did you guys do to Devin? He just showed up.
He looked early, actually.
Did he?
Yeah.
Oh, no.
And,
Yeah, and I think that's just because of how the
So Mercury to self should flow. The other thing that's really about it now is you do the stratosphere, but you don't want Mercury to get.
Right, so.
Yeah, so I mean, I don't think production should really be this complicated. We went through a phase where we didn't need the restriction, even with regard to the oxidation and you know, it's the actual range, and it's probably different. Product, we know that.
Well, that's true.
It's actually, I mean, there's no.
Right.
Right there, so the question is like, how much would it happen in the end?
Well,
And so they like, the amount of oxidation, yeah. But it's just like, there's so much less from zero that like, but I know from dry chemistry, it's shorter.
well, that's
So-
right, but.
So like, the rate is higher, but I don't know, it's hard to.
Turn up, no, like the advanced can turn up production. If you just turn up oxidation, then you increase free Mercury.
Yeah.
Can we try to get in this file?
This is oxidation operates on the elemental stuff.
I mean, the system is pretty linear, so.
There are, we always, just do the reduction.
To go to, you want to go lunch?
I think we should go back to the.
I also may need to, my questions. I go later. About this? So what is today the current, where am I supposed to hold it? Because the microphone. Yeah, have you turned it down? No, don't change it. I'm just.
I think, just, yeah.
There's like signal to me if I'm
It's gonna be.
Or Dan, maybe one of you can speak and.
We'll talk to,
this section that you're trying to get
right after we're done. After I talk a little bit.
Going great, how are you? I just.
What's going on?
So you want to
Ready to go?
download.
What's that? Yes. Have you been there before? I know, I feel like a speaker.
An overpriced speech.
Yeah, so I think we have, I was on point, this is the PC Mac, we have.
Okay, yeah. I'm done downloading everything. Yeah, so it has all of them, but you can go through. Sorry.
So I think if we could just work out what the next elements to show where it's going to be.
Who's doing
Or I don't know who honors to.
What does the list say? The list
Said you were doing posters, Dan. Wait, that's Tuesday. It said you were doing Mac PC.
Okay.
While you're doing posters. So it just means at the end of the session,
Hi there. Can I ask you to help me check if my slide is there? Because actually uploaded a few. I was confused like which one you actually use. Because I uploaded the PPT and then PDF and then
so if there's a PPT,
Yeah, so you just need to switch.
Okay. Yeah, but just like in case you're losing that. That one.
The next one, the next poster session.
Yeah.
Oh, so you probably use the PDF then, eh? PDF, yeah.
Yeah, but I actually upload my poster and my intro slide together under the,
Okay, I can see mine too. I figured if you were gonna check, I'm gonna check.
Thank you.
There were a few that.
If you want to put everything on my computer again, just in case. Because why not?
So, is that? Can I have your schedule?
Oh,
or I'll
yeah.
copy them.
No, yeah, take it, and I'll move my stuff in like one set, and you can sit here. It's the best. I mean, that's the best.
Well, they're really keep me moving. Back and forth.
Yeah, the first session. Save time.
So just have us. They switch things like that. So yeah, you got that.
Good or bad? You just get a bad.
In a sort of formal intellectual sense.
Okay, I'll figure it out.
It's on now.
The mic?
Guys, people from the library take one for
So I emailed them back and said, no, we don't use. Then I said, let's CPF and HDF. So they didn't so I emailed them back again to say, perhaps we have different scale of problems as we used to do that. You know, we have quarter of petabytes. And we don't really get excited about 10 petabytes. No, it's just the university that's doing it. It's doing some sort of data audit kind of thing. It's supposed to be digital archivist or archaeology. So I don't know what they have. Yes. And that'd be for pictures. So I kind of said, so they said they want to sort of put file formats. And then I said to them, so my file formats for Python, but the file format for Python is ASCII, and ASCII file editors. So, but it's like Fortran, like doing a file for Fortran's ASCII file. But if you give it, you give it input files.
All right, so guys, welcome to the session of the Regional and Global Air Quality. I'm Amos Lai from the Chinese University of Hong Kong. We will have one session. So first, let me introduce the first speaker, Shannon Koplitz from Harvard. And she's going to tell us about the impacts of Southeast Asian coal emissions on air quality. Please take it away.
It is, yeah, okay. Good morning, everybody. As Amos said, my name is Shannon Koplitz, and I'm a fourth-year grad student here at Harvard working with Daniel Jacob and Loretta Mickley. And today I'm going to talk to you about some work we've done to assess the burden of disease from rising coal emissions in Asia. And I'm actually not going to be talking about coal emissions in India and China. Emissions in these two countries have been increasing really rapidly over the past couple decades and have consequently received a lot of attention, which has perhaps overshadowed the rapid coal expansion that's happening in other parts of East and Southeast Asia as well. So I'm actually going to be focusing on those other understudied countries. And I also wanted to say, so the focus of my work here is using Geoschem as a tool to quantify the particulate matter and ozone changes coming from these coal emissions. But kind of the broader agenda, both for our collaborators at Greenpeace and our funding source, the Grow Old Family Fund, is actually targeting the carbon emissions from this coal. So this project has been an opportunity for us to participate both in the conversation about global climate change and global energy policy, but speaking in terms of human health effects. But in order to do that, to say something about the health effects coming from these coal emissions, we need to first know what the emissions actually are. So the first part of this work was basically compiling as much information as we could about the presently operating coal power plant fleet in these countries. So that's including information on everything from the currently implemented emission control technologies, the type of coal being combusted, the power generation at each facility, et cetera. And then using that same kind of methodology and that same kind of framework, we also built a plant level emissions inventory for all of the projected coal plants that are in the pipeline right now for all these countries. So that's everything that's listed as permitted, approved, under construction, basically anything that, that these countries have on the books. And it's kind of based on projected estimates for the timeline it's going to take for all of those plants to make it through the developmental process. We're estimating that that's going to be, it's possible that all of this capacity will be online by 2030. So we have these two emission inventories, then we have one for the currently operating fleet and for what could happen by 2030 of SO2 and NOx emissions coming from these coal plants. We care about SO2 and NOx because they're precursors for particulate matter formation and also, in the case of NOx, for ozone formation. And when we compare our emissions estimates for those two inventories, we see about a tripling potentially between the present day emissions and what could happen by 2030. Which would bring the emissions of coal plants in these countries above the US level emissions. Coal emissions in China and India are probably still going to go up. I think maybe by how much is potentially a matter of debate still. But the US emissions are going down. And most of this regional increase that we're seeing in our calculations is coming in Indonesia and Vietnam, which are two countries that are also undergoing very rapid economic development and population growth as well. And so the situation by 2030 is going to be one where you have even more people living next to even more emissions. So what we wanted to do in this project was to try to quantify both for the presently operating plant fleet and also for all this projected capacity by 2030, what do these coal emissions mean for human health? And the way we did that was we used GeosChem version 902 at the nested resolution over Asia, so the 1/2 by 2/3 simulation. And we implemented into GeosChem these two scenarios of coal emissions in these countries. So this kind of our best guess at the present day, the 2011 inventory, which is kind of our best guess at what the currently operating fleet is emitting. We also implemented what could happen by 2030 if all of this projected capacity comes online. And then we ran a base case scenario where we basically just removed the contribution of these coal plants to emissions in the standard anthropogenic inventories used in GeosChem. And we ran a year-long scenario a year-long simulation for each of these different emission scenarios using 2011 meteorology each time for consistency. And then from there, by taking the difference in the results from these different simulations, we can attribute changes in particulate matter and ozone that are coming from coal emissions in these two cases. And then from there, we can apply kind of empirically derived concentration response functions from the literature to try to estimate what the premature mortality is due to this coal-related pollution. And what we see in terms of the regional pollution is, in general, and particularly in the case of the PM, the enhancements in the pollution are happening near densely populated centers, particularly for the case of Hanoi and Jakarta. In the case of Hanoi, the enhancement in PM 2.5 that we're seeing from the future coal is about 12 micrograms per meter cubed in the annual average, which is a pretty big enhancement. And we're also seeing, even though we're not directly accounting for changes in emissions in China, we see the 3rd highest total exposure in China just because there are so many people in southern China living next to these increasing Vietnamese emissions. Okay. And so once we have those changes in particulate matter and ozone, we can try to say something about the change in mortality due to this pollution by incorporating information, some assumptions about kind of the baseline mortality rate, some empirically derived dose response relationships from the literature. And actually, I think Bonnie Ford is going to talk a little bit more about the uncertainties associated with this whole process. But for now, this is kind of the standard approach. And then we incorporate our PM 2.5 and ozone fields from GeosChem. And what we estimate is in total, about 16,000 deaths every year from the presently operating coal fleet, increasing by about 26,000 deaths up to this projected 2030 capacity levels. And so altogether, if we also include an estimate of about a 10% increase in population in both Indonesia and Vietnam, we calculate about 45,000 deaths every year if all of this projected capacity comes online. Okay, and just for comparison, in the US, I saw an estimate that says it's about 8,000 deaths per year from power plant PM. So this is kind of the take home, but I also just wanted to mention that we did, based on kind of the size of the regional perturbation, we may be expecting to see some global influences as well, particularly maybe in the tropics or the southern hemisphere, just based on the location of the emissions. But in general, the global changes we're seeing in PM and ozone are pretty small. But the spatial patterns of the enhancements over Europe and the US are consistent with what Eric Leibensberger in his 2011 work attributed to changes in NOx emissions from Asia. So these far field enhancements are being driven largely by the oxidant, changes in the oxidant chemistry, as opposed to the regional case where a lot of that's probably coming just from the SO2 emissions oxidizing to sulfate. And so with that, I think I'm out of time. Thanks, I'll take any questions.
Interesting. So the concentration response functions used by Dan Kruski did not have knowledge about what happened at higher concentrations and tend to assume a linearity out at higher concentrations, which would overestimate the associated burden. There's a more recent study put out by Rick Burnett and Aaron Cohen that's informed by smoking and indoor air pollution that saturates at higher concentrations, and that may be a more realistic concentration response.
Right, so we actually capped with no further effects above 50 micrograms per meter cubed. And we tested a couple other approaches, so the global burden of disease approach, and also a bigger, like a linear response from the EPA, from one of the other EPA studies. And we did see, when we used the global burden of disease approach, we got a few slightly lower estimate, at least in terms of the response to the PM. But it would still be kind of in this ballpark of 40,000. So yeah, I think exploring maybe the sensitivities to the assumptions we're making about doing this calculation is something that's important, but I think we'll still be in this kind of 40,000 ballpark, yeah.
What kind of emission control are you assuming for SOx and NOx?
Yeah, so that depends. When that information is available for the plant, we use that and make some assumptions about what the emission control would mean. So whenever possible, it's a plant level assumption. We also have the company level data. And in general, so I have the whole spreadsheet, and I can, if you're curious, I can check that for you offline. But in general, the estimates here were conservative on purpose, just because of the potential policy implications of this work. So when in doubt, we tried to be conservative in our estimate of the emissions.
Conservative meaning higher.
Meaning lower.
In that global map you showed, Dan, what was that hotspot over Denmark in 2030?
So this is well, I should say, so this is the emissions everywhere else are still at present day levels. So this is our 2011 global emissions. And actually, I think the European emissions are slightly outdated in the version of the model we're using. So if you were to do this with version 10.01, you get slightly lower emissions over Europe. Well, probably you have higher domestic sources of one of the precursors. I'm not sure exactly which one, but yeah, SO2 NOx, ammonia. I can double check if you like.
Is it an interest of time? No, it's a change in oxidant.
Yeah.
So it's where SO2 is emitted.
Yeah, or any other the PM precursors. If you have more domestic precursors and you have an increase in the oxidant chemistry, you'll bump up your PM.
So in the interest of time, I think we can move on. Thank you very much, Shannon. Next, we'll have Jin Tai Lin from Peking University, who's going to tell us about global pollution and transport.
Thank you. Okay, I'm Jin Tai Lin from Peking University. So today, as you can see from the title, that what I'm trying to convey here is to rethink global air pollution and transport, and rethink pollution and transport in a multiple fronts. Oops, this one. So first, let me thank my collaborators and funding agencies. So we go on to this beautiful animation of GeoSCAM, global GeoSCAM, a 200 kilometer resolution. This is a typical resolution for a typical global model. And it's very beautiful. The plot is very beautiful because it shows the transport of carbon monoxide in the troposphere, middle troposphere, from one area to another around the globe. So we know that very clearly pollution is a global problem, not a regional problem, not just a local problem. However, my question is this figure really very accurate? The answer is probably not. It's not because we know that emissions, we really don't know exactly how much we are emitting CO in the atmosphere. Also, we don't know if we really understand all the chemical mechanisms in the model. But of course, in this particular study, I'm trying to, a particular point I'm trying to convey here is the small scale variability that's missing from this beautiful global simulation. And by small scale variability, I mean the scale that's smaller than what the model can resolve. For example, the urban rural chemistry, nonlinear ozone chemistry, for example. So of course, we all want to have a better framework, model framework to capture all this small scale variability, hopefully globally, but it's costly computationally. So there's ways to reduce the cost. It's very good, but it's still very difficult to do. So on the other hand, the regional model community have derived this brilliant idea of capturing the small scale variability in a particular region, in this case, 3 regions in the world, covering all the major source regions. But this nested model does not affect it. This nested model takes lateral boundary conditions from the global model. That's all the typical setup. So what we do is to think, why don't we use the nested model result, which is better captures the small scale variability, to modify the global result within this representative domain, and that's what we did. But just simply doing that, we found that we are improving model results in many ways consistently. For example, we reduced the OH concentration by 5%, which is much larger than the interannual variability of OH. We also increased the lifetimes of methylchloroform and methane. We reduce ozone, we increase CO. On all these changes, as I will show later, and here, that it's actually led our simulation much closer to observations. And I would think this is very important. For example, for ozone, you can see this is for 2009. I would compare ozone vertical profiles with Mosaic and Hippo data. As you can see, red is a two-way model, blue is global model, and basically, you can with your eyes you can see the two-way model is capturing much better the observed ozone profile in black. For CO, similar story. I'm not going into detail, but basically, the yellow line is the Hippo data, a black line is global model, and the red line is two-way model. Again, two-way models capture much better the Hippo data, all seasons, all 3 years, than the global model. And if you look at the green, that means that if I want to use the global model we want to increase some emissions so that our model result can match two-way coupled model or observation. And that's how much I have to increase globally. So it depends on the campaigns. It could be 15%, it could be 35%. And we think this has huge implications for CO emission constraint, for example. For the folks who does not care much about chemistry, they maybe only care about, say, black carbon, which does not have very active chemistry. This plot just basically shows that by doing just this simple coupling, we actually improved a lot on the surface species black carbon simulation. For example, in the enlarged area is the Tibetan Plateau, where two-way model reduced the black carbon by almost 50 or 40%. And we already know from the black carbon modeling community that global model tend to overestimate black carbon, surface black carbon in this particular region. And if you go back to the global domain, you can see that there's a large impact on the Arctic regions, etc., etc. And that will be, I think, very important for the global, for black carbon simulation. So if you have more interest in our two-way model work, please go to my students' talk next tomorrow. So let's go back to revisit our understanding of the pollution over the source region. And in this case, we are revisiting the SETI measurement of NO2, tropospheric NO2. And NO2 is very important, SETI is very important, so I don't want to elaborate that. However, we derive a new retrieval called Pomino. And we are not doing it for fun. We're actually doing it to improve several major parts of current retrieval. For example, we explicitly consider aerosol optical effects in the retrieval. This is the only one. So far, this is the only one retrieval. They really considers explicit aerosols. And there's other parts that I don't want to go into detail. And the data is publicly available. So this is just some comparison, shows we are doing great, so just pass that. Let's rethink the global air pollution transport problem again. As atmospheric scientists, we understand that pollution is produced because of the economic activities, industry, power plant, transportation. That this process emits a lot of stuff into the atmosphere, and it will, but via atmospheric transport affect the downwind region. In this case, it's the consuming region. However, this production is driven by consumption, basically. So by this mechanism, the consuming region is actually moving a lot of production and emissions to the producing region. So this is, I think, is a more complete picture of what is going on regarding global air pollution transport. For example, if you look at China's pollution, okay, sure. Just 10 seconds. Okay, export-related Chinese pollution account for 30% of China's sulfur pollution, and this pollution will be transferred a little bit to the downwind regions. So, basically, I'm summarized here, and this kind of analysis is kind of trigger some interest in the National Academy of Sciences. So we won this particular award, Best Paper Award. Thank you.
Because all of your nested grids are in the northern hemisphere and the southern hemisphere. They're very different processes like biogenics.
The short answer is yes, we did, and the model improves on a latitudinal basis. So yeah.
One short question, perhaps. So what specifically in the two-way coupling is causing such a big difference in the global? What is the specific mechanism?
But basically, it's related to, I think, most important one is related to the nonlinear ozone chemistry, production and loss.
Right. So thank you very much. Next, we'll have Christopher Miller from Harvard. He's going to tell us about VOC emissions from the Pearl River Delta where I work.
Sorry. Okay. So yeah, I'm going to talk about some space-based constraints we've been making on emissions in the Pearl River Delta. And I would just like to acknowledge my advisors, Daniel Jacob and Kelly Chance at the Harvard Smithsonian. So by space-based constraints, I'm actually talking about just glyoxyl and formaldehyde. So both these species are produced from the oxidation of VOCs, and they have very short lifetimes. So they're basically traces for their emission. And as you expect, their distributions are quite similar as shown in these maps from OMI. But if you take the ratio, that ratio varies by spatial location. And this is because different VOCs will produce glyoxal and formaldehyde at different yields. So we can potentially use this as both these products as combined constraints to potentially constrain VOC speciation of emissions. But one of the problems that we've had is that when we've been comparing surface observations to our model and satellite observations, even when we can get the surface observations consistent with the model, the satellite observations from other products have been overestimated. So a lot of our work has actually been going into improving the glyoxal retrievals. The bottom line is that they're now significantly lower. And if you're interested in that, then there's a really long paper in AMT that you can look at. So we're actually initially interested in using the retrieval to study isoprene oxidation chemistry, but we got really distracted when we saw this huge enhancement of glyoxal at Amos's house. The PRD is actually, it's colloquially referred to as the world's factory. It constitutes about 20% of China's exports, including some of its pollution, I guess, from Jintai's talk. So we were really interested in understanding what's actually going on here. And if we look at other satellite products, so this is formaldehyde, we see that there is an enhancement in the PRD, but it's similar in magnitude to other anthropogenic regions, and the same goes for NO2. So there's something really esoteric about glyoxal. So just to get a back of the envelope calculation, we took a recently published high resolution inventory of VOC emissions. And for each species in that inventory, we ran it through a chemical box model driven by MCM chemistry. And we calculated basically average production rates for both glyoxal and formaldehyde. And according to the inventory, most of the glyoxal is coming from aromatic emissions. And a lot of this is actually from solvent emissions for a lot of industrial processes. If we look at formaldehyde, it cares less about which particular species it's sort of being produced by everything. Another thing we can do is we can separately grid the data by wind direction, so what I'm showing in the top left plot is glyoxal observations that have been gridded when the winds are blowing over the PRD from the northeast. And we can run trajectories through that plume and then integrate across those trajectories to get a line density as a function of time, as shown on the right. And we can use this to try and get a rough idea of how well these bottom-up emission inventories are doing. So we just use a simple 1D plume model where we have the emission of a VOC. It gets oxidized downwind to produce glyoxal, which then undergoes further oxidation. And if we use the estimates from that high-resolution inventory, we get reasonable agreement between OMI, probably within the measurement uncertainty, which is usually around 20 to 30%. And we can also do the same thing for formaldehyde, and the PRD inventory does reasonably well. And we can play the same game for other inventories. So what I'm showing here are two other inventories that are relevant to GeosChem. REES version 2 is probably like a state of the science regional inventory. And we see ballpark agreement, but when we look downwind, so toluene has a slightly longer lifetime, and we see that maybe the toluene in the REES model is the higher levels are not supported in the observations. What's more interesting perhaps is that if we look at retro, we see these large underestimates, particularly for aromatics. So the question is whether this is confined to the PRD or if it's a more regional underestimate. So we can look at the model like GeosChem, which is run with a retro inventory, and compare it to OMI. And we can see that there are large underestimates in glyoxal in China. And a lot of this is probably just due to the fact that retro stopped estimating emissions at 2000. And since 2000 to 2010, there's been pretty large growth in economic growth in China. And so we can also look at other inventories that are from this period, and we can see that gradually, as a function of publication date, aromatic estimates have been rising. So between retro and the inventory to support Intex B, aromatics roughly doubled, and then they increased again between then and REES by a factor of 2. So there's been one previous study by Yuhong Wang's group, I think, who studied, who looked at Skier-Markey observations of glyoxal to try and constrain Chinese aromatic emissions using the Intex B inventory, and they found that they had to increase Intex B by a factor of 6 to be able to match their observations. So since then, inventories have been revised upwards, and the model columns are now lower. So we're sort of seeing that, at least for this regional case study, things are roughly consistent. So now we feel we have a better understanding of the aromatic sources, so we can better assess their potential atmospheric chemical implications. I think I may have failed to mention that they're quite prominent pan precursors as well as SOA precursors. So they could potentially have some interesting, things. So I'll just leave it there, I guess.
Any question for Chris? Yes, Bill?
So it seems like your the satellite columns are dropping off more quickly than you would expect based on the production from those precursors, right? Is that a function of the precursor emissions, or the glacial loss?
It's a bit of that, and it's also our assumptions about the diurnal scaling of the emissions. So I think particularly for REES, a lot of the toluene is buried in solvent emissions, which we've kind of assumed as a fixed source. But I think REES has a problem distributing traffic emissions. It sort of smears them over the whole Guangdong province, which that would affect that diurnal cycle and probably push it more to the left. If that makes sense.
No other question? All right, so I thank Chris again for carrying well the region. Next we have Aaron and Dr. Lar from NAPLC. He's going to tell us about combining geochem with satellite for improved PM2.5 population exposure estimates. Please take it away.
Well, thank you very much. Oh, wrong one. All right, so fine particulate matter, PM2.5, as many of us know, has some pretty significant impacts on health and longevity. It's also been found to be a fairly cost-effective way for governments to improve the well-being of their citizens in many cases. But despite this is a growing problem in many parts of the world, and is expected to dominate environmentally related mortality by 2030, or according to some more recent reports, maybe perhaps already does. So with this as motivation, one of the main research goals of our group in general, at least a number of members of our group, is to develop improved estimates of PM2.5 around the world, as well as domestically. One of the main ways in which we do this is we use satellite retrievals of aerosol optical depth, and use GeoSchem to relate that to near-surface PM2.5. Most recently, what we've done is extend and develop an optimal estimation retrieval, which combines GeoSchem and MODIS more directly. So essentially, for those of you not familiar with optimal estimation, what we do is we take what you might consider more standard, more pure satellite retrieval, if you will, and we constrain that using aerosol optical depth from GeoSchem based upon the relative uncertainty between the two. We then go ahead, take this improved estimate of AOD, relate that to PM2.5 based upon the AOD to PM2.5 relationship from the model. In practice, this is just taking the ratio of PM2.5 to AOD from GeoSchem. There's a lot more that goes into that. It's deceptively simple. Basically, it's largely a function of vertical structure and where is that aerosol distributed? Is it aloft, the surface like that? Also, aerosol type, how scattering relates to mass, that sort of thing. So in essence, we use GeoSchem both to constrain our AOD retrieval as well as to relate AOD to PM2.5. Then we use satellite, in this case MODIS, as an observational constraint, as well as provide higher resolution, in this case down to about 1 kilometer, something we really couldn't practically simulate, obviously. So how do we do? So here we have our here at the top left here, you have the in situ values observed over Canada, the US from 2004 to 2008. In the middle, we have GeoSchem just by itself, and you have our optimal estimation values on the right. You can see spatially, they all look broadly similar, which is always encouraging. More direct comparison at the bottom here, you got scatter plots of GeoSchem versus in situ. and OE versus the in situ. See, GeoSchem all by itself does fairly well, so an R squared of 0.57 versus OE, which shows some improvement, so an R squared of 0.62. But the real major gains come in terms of the magnitude of PM2.5. If you look at GeoSchem, we've got a high bias, slope of 1.5 there. There's a negative offset with that, of course. Root mean square difference of 3.8 versus the OE, which shows a slope of 1.1 with root mean square difference of 2.6. Those benefits really come in part, for no small part, from the OE retrieval we've developed. So if you look at your standard MODIS products, the high resolution 3-kilometer product, we found to be fairly noisy. So if we directly correlate AOD to PM2.5, that's not relating it there. We just seen R squared of 0.18 in that case. The more robust 10-kilometer product does a fair bit better. R squared of 3.8 for our 1-kilometer estimates, 0.41. GeoSchem interestingly actually does better by itself just if you're correlating AOD to PM2.5 with 0.44. But that is more than made up if we go ahead and relate it directly to PM2.5. Interestingly, despite having done all this at 1 kilometer, we didn't see much benefit to that. So if we go through and just spatially degrade our 1 kilometer estimates to 3, 5, and 10 kilometers, you see our agreement remains the exact same. So it speaks something to some of the uncertainties we're dealing with. Not surprisingly, GeoSchem stays the same. Of course, it's at about 50 by 70 kilometers in this case. So the big question is, how do we do better, right? And so we want to do better. And so what I've plotted up here is the residual bias between our OE estimates and the in situ PM2.5. This is just the difference between the two. See a number of features within this. So if you look in the West, for example, you see a high degree of variability. See overestimates right beside underestimates, things like that. In the East, you tend to see more large-scale regional features. So you see a large-scale overestimate in the part of OE in the Ohio River Valley. South you see a large-scale underestimate. So what we decided to do is develop a statistical model, see if we could predict what's causing some of these biases to help us motivate what directions do we need to do further improvements. For those of you not familiar with geographically weighted regression, essentially what it is, it's your standard linear regression, which most of you are probably familiar with, but rather than assuming that your predictor coefficients are constant, you allow them to vary in space. So what we're going to do to try and predict our bias is use predictors of percent urban, elevation difference. Elevation difference is specifically looking at resolution. So we're taking the difference between the elevation averaged at 1 kilometer resolution compared to the average elevation of the GeoSchem resolution of 50 by 70 kilometers in this case. We're also going to use various speciated components as predictors as well. So nitrate, primary carbon, and secondary organics. You notice we did not include sulfate in this case. This is partly a limitation of statistical methods where things look too similar, the methods get confused. But also a statement of confidence, and most of our comparisons suggest that sulfate's doing fairly well. So we tend to believe our uncertainties might lie with some of the other factors. So we go ahead and run that GWR, we can get a predicted bias surface such as up here, and you can see it agrees fairly well with the observed biases. Perhaps more interesting than the surface itself is what's driving that bias surface, what's contributing to this overall surface. So here we've got the contributions, so if you sum all these up, you get this one here. So here we've got the contribution from elevation difference up here. You can see again lots of fine scale variability in the West. We got lots of mountains, so that's not unexpected. I can see percent urban here, hard to see on the big scale. You see in some urban centers, for example, you can see hotspots where there's some elevation going on there. You'll see some large scale biases tend to be associated with specific species. Now it's important to stress this is not directly saying there's a bias in GeoSchem of those species, but more in the way we're using it. In most cases, it probably has more to do with the vertical profile itself. But this provides a nice spatial structure with which we can extend those observed biases to produce a better surface where we have ground monitors available. So if we go ahead and then apply that surface, apply our predicted bias to our original OE estimates, we get surface such as you see up here. That's our residual bias, not surprising, of course, it's much reduced. If we go and then do a comparison, just a direct scatter plot again, of course, you get fairly good agreement. Again, not too surprising given it's been calibrated with the model, so an R squared 0.82. But we also did hold back some sites to see, okay, well, how do we do in the absence of monitors? And we see fairly similar improvement in the absence of monitors over again in North America, so an R squared of 0.79. What's of particular note, after we go ahead and apply this, is we then do see benefits of high resolution. So here, again, we've got over different regions, so all of North America, Eastern North America, Western North America. Take our 1 kilometer product, degrade to 3, 5, and 10 kilometers. You can see very clear trends of, our agreement goes down, so R squared decreasing, mean square difference goes up, things like that. Which drives some motivation, of course, for GeoSchem. As we push to higher and higher resolutions, there are things we want to capture in there, and we'll continue to find more, I'm sure. But I will just leave it at that and leave the just basic conclusions up and turn to take questions then. So, great. Thank you.
If you were to take your same regression here and then apply it to Europe, where you have enough 2.5 monitors where you could
We're working on it. So the one limitation of working at 1 kilometer is it's very, very slow even to run our OE estimates. So we've got Europe is churning through very, very slowly. And obviously the hope is to do something which is more globally applicable, right? So I think the big strength when you start bringing the satellite is this global applicability. North America, yeah. No, that's the thing with yes. So yes, this is for North America only. And it's the thing with geographically weighted regression is in allowing those predictor coefficients to vary in space. You're inherently tied to where you have monitors to some degree. Now, how far you can deviate from those monitors is always a big question. And so what you could do, and I have done this and had some success with it, not as much, was basically get away from geographically weighted regression, just go straight linear regression. Then you can start getting to maybe global constants.
Spaced by things like SOA, nitrate, and elevation that you have around the globe. So in theory, you can apply this.
Sorry, I missed part of what you said there.
They're tied in space through things like SOA, nitrate, and elevation information fields that you have.
They are, yes, so they are tied in space to some extent, but so that's where the difference is between, so your predictor, we have all the varying in space. The predictor coefficient is different, right? And so that's what we're allowing to vary with geographically weighted regression. We can talk more later, but yeah, Chris.
Are your regression coefficients stable over time? Is there major changes in SOx, NOx, and ammonia emissions?
They are allowed to vary by month. So every year holds the same. There would potentially be some variation in that. So that's why we kind of limited the period we did. We have actually started to investigate further afield as well. And we see some of the coefficients changing. So it's an inherent limitation of this. But part of what we try and do is provide, again, the best estimate we can at PM2.5. And what we found is that while globally, I mean, just using satellite and geochem as we've traditionally done works, I would argue about as best as you can do. But there are obviously limitations. In some areas, such as North America, it's been really enforced in the past. We haven't tied into the ground monitors because there's a wealth of information obviously there. And so what this is trying to do is see, okay, starting from our satellite model product, how can we then bring in the ground data and then learn from it to help inform a better global product in the end? And so that's more what this is trying to do.
Thanks, Erin, again. Next, we'll have Bonnie Ford from Colorado State University. She's going to tell us about the uncertainties in estimating health effects of PM2.5 exposure.
All right, thank you. So I'm Bonnie Ford, and I currently work for Jeff Pierce at CSU. This is work that I did with Colette last year, looking at uncertainties. Specifically, I'm going to be talking about calculating burden estimates from chronic exposure. And so the motivation for this work comes from this statement that we often use, that exposure to particulate matter has negative impacts on human health. Specifically, it's associated with an increased risk of premature mortality. If we look through the literature, we get different values for this burden estimate, and the way in which we calculate that is going to be different. Also, that second motivation is this work that's done by Aaron von Dockelhaar, working on developing the satellite-based PM2.5. If you talk to epidemiologists, this is really exciting work, and it's been used in a whole bunch of different health studies. So taking the exposure estimates and using it to calculate the burden of disease, which I'll talk a little bit about, global childhood asthma, lung cancer, diabetes, mortality in rural regions. And so this is really exciting, but we as people who are really interested in improving the model and improving representation, want to ask these questions about, if we're making improvements to the model, how does this potential model uncertainty in the model impact these results? And this is going to be more focused on this earlier version that Aaron developed that's been used in these studies, and how the model uncertainty might compare to other sources of uncertainty in these estimates. So there's different factors that are going to influence these health burden estimates. Obviously, the PM2.5 concentrations, the values that we get, where we get those values, and are going to be important, and how we get those. So if we're using a model or if we're using the satellite-based, also the risk ratios that we get from the literature, and the concentration response functions, which I'll talk a little bit about, and also the population data that we get. So who's being exposed and what are the characteristics of those populations, which I won't be discussing here, but is obviously a source of uncertainty. So if you look through the literature, you get different values for this burden of disease, so the estimated premature mortality due to exposure. So we have here just a few examples for the US and for China. And so Aaron talked about the newer version of this satellite-based PM 2.5. And again, he's using this, the model to relate the PM 2.5 to this AOD. And these factors, this is going to be a function of vertical distribution, the aerosol types, optical properties, and the meteorology. And this is really important for any kind of method that tries to relate AOD to PM 2.5. So we wanted to look again at some uncertainties in the model. So we did sensitivity tests in the model. So all I'm showing here on this page is just model to model comparisons. And so we looked at different factors. Obviously, there are a lot of uncertainties in the model, which we've discussed here. But these are just a few that we looked at. So looking at variability in AOD and ADA. So if we kept these values constant over a season, how would this change our annual average concentrations? We've done this on shorter time scales as well, but I'm just going to show you here for the annual average concentrations. We also looked at the impact of the vertical profile. This is really important. Here we're actually testing the variability in the vertical profile. So if we kept the shape of the vertical profile constant through the season, and we allowed the mass to change, but it had to keep that shape, what would be the impact? Also using this average relative humidity profile, and also if we didn't include nitrate in that estimation. Nitrate's overestimated in the model in the US and in Eastern China, and it has a different vertical profile than a lot of other species. We also tested the optical properties, but we did this in a really simplistic way. So we looked at if we assumed all the mass in the column was sulfate or all the mass in the column was black carbon, hydrophobic black carbon, which has a higher mass extinction efficiency at lower relative humidities, and sulfate has a higher at high relative humidities. And we also looked at the model resolution in that we calculated our ADA values for the 2 by 2.5 degree and then degraded them to the nested resolution. And we calculate this for a whole bunch of different regions in the US and for China. And you can see that there's a lot of regional variability. The variables that are important in different regions change. And we also see some differences in if we're introducing random error that has to do more with the meteorology, so removing some of that variability, or if we're introducing more systematic biases, making assumptions about aerosol types. And you can see some of those differences. Those biases that are more systematic aren't going to be averaged out even when we're looking at longer averages. We also see that it's really important not only to simulate these kind of seasonal averages, but also to get a lot of this variability, which is important because often when we do our comparisons, we're looking at these kind of averages to try to get rid of some of that random error. The other part of this uncertainty is actually the concentration response functions that we use and the risk ratios that we get. So if you look through the literature, you get a variety of different risk ratios determined from different studies. And so this is just showing a few for lung cancer. You can see here the risk ratios on this axis. So anything above 1 would mean that it's an increased risk. If there's 1, that there's no change in that risk. The ones that are most often used are this Pope 2002 study, which was the Harvard 6 Cities study, or the updated Layden et al., and also the Krusky et al. Study, which was the American Cancer Society study. Also, what's really important is how we think that that risk changes at higher concentrations. So do we assume that it's linear, it just keeps increasing, or do we think that it peters off at higher concentrations? And in what way does that end up kind of leveling it off? Do we just use a ceiling value, or do we use a exponential function or a power law? So there's different studies that suggest different values. Also, do we include a threshold value? Is there a value below which we don't see any effect? And that's not really supported in epidemiology, but most of these studies that are looking at ambient concentrations don't look at really low concentrations. So we calculated the burden for different causes of death here, using a variety of different relative risks from the literature and using a variety of different concentration response functions. So we put these together, looking at this uncertainty comparison. I'm showing here some of these different values from the literature for the US and for China. Also estimates of just using the model and then using the satellite-based estimate. And then we also put our uncertainties here. So if we're just looking at for that model uncertainty, which you can see kind of overlaps that difference between just the model and the satellite base. I want to stress that the movement towards including more observations in the optimal estimation framework that Aaron talked about would decrease this uncertainty a lot. but some of our model uncertainty is going to kind of explain maybe why we're getting some of these differences. If we really look at this too, we see that the concentration response function and the relative risks are really our largest source of uncertainty. And so that's really important to think about how we're applying these and trying to think about the best way to apply those, especially when we're looking at comparisons from different studies. And specifically thinking about the fact that we're using these risk ratios and concentration response functions that were developed for specific studies, specific populations, and it may not be appropriate to apply those in different situations. I think using this for using this product for developing those risk ratios and concentration response functions could help reduce that uncertainty. That's it.
Yeah. I was just wondering if you tested your estimate of error against observation goals. Do you estimate loss observation to actually observe the error estimates representing the observed error?
So we looked at kind of some of what the differences are, but we're not really trying to say that this is like the best way to do this, if this improves it, because we're just like looking at that variability. And so it's not necessarily saying this is an improvement to the model if we do these things.
I was wondering more about the error that you estimated that is observed.
The error just for the model ADA?
For model and just maybe about an error bar, which is going from error estimate
right.
to 15.5 producing. Can you compare against the observation to see if that lines up nicely or how that compares to the observed for error?
Not specifically, but I think that that's comparing two different things because this is looking at how we would actually do that compared to in the model. So I think it's kind of looking at two different things in those errors.
Shannon first.
Yeah, so there seems to be a lot of interest in the community about the optical properties of ground carbon and how we treat ground carbon in GSChem. I'm just wondering, do you think if you incorporated an uncertainty assessment about ground carbon, would that change the estimate model?
Yeah, I mean, I think you can include a whole bunch of different model uncertainties to try to get that. And we were just trying to say, here's kind of the largest range that you would get in these two kind of these ranges. So I think there are a whole bunch of different uncertainties we could include.
One short question.
Okay, so the mean number of that we have is about 2.1 million here. This is about twice as much as the conventional estimate, which is about 1 point.
Yeah, so you see that in the there. There's other estimates.
What's the
what? So
the number is much larger.
So it's going to be depending on the study that you compare this to. So some of the previous studies just looked at urban regions. It's also going to be in, again, how you're applying these different concentration response functions. So assuming the linear one is going to give you a much larger estimate.
All right, thanks, Bonnie, again. And the next we'll have Forrest Lacy from CU Boulder. And he's going to tell us about the health and climate impacts of cook stove emissions.
Okay, thank you for the introduction and allowing me to present some of the results that I've been developing at CU Boulder under my advisor, Devin Henze. I would first like to start by acknowledging the EPA STAR program and support from NASA HEC for the computing support. So first off, I'd like to start with why another cook stove study. There's been a lot of investigations into cook stoves, but a lot of them have relatively cursory treatments of aerosols and focus more on the greenhouse gas impacts. So the reason that we should focus on aerosols is that they're harder to account for due to the spatial variability related to both health and climate metrics. So we started thinking, how can we improve on the level of current understanding by using adjoint modeling methods? So for this study, we're using the GeoSchem adjoint model, version 34, at a global 2 by 2.5 degree resolution. You've been using the baseline year 2000 emissions from Lamarck et al. And we've actually, for our emissions perturbation that we're studying, we've developed a cook stove specific emissions inventory by combining the bond inventory with solid fuel use estimates from Bonjour. So the initial estimation is considering radiative forcing. And that's what we currently have the adjoint model for. But by taking radiative forcing within different latitude bands, we can estimate the total global climate impact using the absolute regional temperature potentials developed by Drew Shindell. And this basically accounts for the fact that a zonal change in radiative forcing will produce the same climate response within that same zonal band. An application of this, we've seen that if you remove all biofuel emissions, using the ARTP method, you get a cooling of 0.22 degrees using the ARTP method, while you get a cooling of 0.13 using the global method for this. The reason for that is that the Northern Hemisphere mid-latitudes and the Arctic are much more sensitive to changes in radiative forcing, and that's why we see that approximate doubling. In addition to using the direct radiative forcing, we've also calculated scaling factors which we're applying to our sensitivities based on following the same methods used in the UNEP integrated assessment report. So this table is showing our scaling factors not just for the direct effect, but also for semi and indirect effects for the different species. An additional effect that we've included in this is the radiative forcing due to black carbon deposition onto snow ice changing the albedo. So for this, we've developed the adjoint for black carbon deposition onto snow and sea ice and spatially distributed that effect as shown in this plot here. So now kind of onto the results. By combining all of the adjoint radiative forcing sensitivities along with our scaling factors and the black carbon deposition adjoint, we've estimated a global temperature impact due to removal of all biofuel emissions. So the plots that you see here, each color is representing your assumption of radiative effect for black carbon. So we have black carbon weak, black carbon central, and black carbon strong. Within each plot, we also have a range of assumptions for your organic carbon radiative effect. So again, here you can see strong, mid, and weak effects relating to the height of these polygons. And then finally, on the x-axis, we have a range for the black carbon to total carbon emitted from cook stove sources, which we've called phi. And by combining all of these, you can see we go from a 0.16 degree warming all the way down to a cooling of 0.28 degrees. And the central estimate is a 0.05 degree cooling. We can take these results and aggregate them to the country level scale. And this is the resulting plot from that. You can see that India and China dominate this with approximately 80% of the total climate impact. But you see a lot of countries in the southern hemisphere and tropics don't have a large effect, whereas some of the higher latitude countries do have a larger effect. And in addition, you can actually see that Mexico and Brazil have a central estimate of a warming effect. So you can rank these countries by both emissions and temperature impact. And you see with the exception of China and India, it's not a direct response. You see many countries with high emissions that don't have a high temperature impact. So why is there that difference? So here, we've taken each individual effect for the organic carbon, black carbon, semi-indirect effects, and snow ice albedo, and plotted them by country. And we see that in countries that have higher emissions, they tend to have more centralized range, and they also have larger organic carbon effects. Now, for the cook stove exposure, which we're relating to the health impact, we can do the same thing where we're using our adjoint cost function as population-weighted PM2.5. So here you can see a number of countries that have large contributions to ambient population-weighted PM2.5, but this one does follow the emissions very well. You see India, China, Bangladesh, and then a lot of the African countries standing out, along with Mexico. and that's due to the population density there. So another way to quantitatively think about this is to combine these two effects. So what I've done here on the x-axis is put the percent contribution of each country to the climate impact, and on the y-axis, the percent contribution to the exposure impact. And the bubble size is scaled by the summed impact. So the advantage of this is that you can look at two countries with a specific focus in mind. So if you look at Pakistan and Uzbekistan, they have very similar combined impacts. But if you're trying to control for the exposure or health impact, you would rather target a cook stove intervention in Pakistan. So I'm out of time. I'll leave my conclusions and main points from this study up here and field any questions you may have.
How, what fraction of the climate effects came from the deposition of snow relative to the atmosphere?
You can kind of see that here. It's a relatively small amount, but in some countries it's equal to the direct radiative forcing effect. So if you look specifically at Nepal, it's equal magnitude to either the direct or indirect effect.
So have you considered the indoor air quality as impact associated with the snow in the study?
So that basically kind of the motivation behind this was that indoor air quality is something that has been well studied. So for different stove interventions, they have a good understanding of those indoor health impacts. So we looked specifically at the ambient. Elise?
So it seems like always a trivial question, but for African countries, the census data is really poor, so the population estimates are wrong. How sensitive are your results that the population appear to provide to those?
Right. So the current level of this study, we have a lot more detail on the estimation of climate impacts, and it's kind of on my conclusions. Whoops. No, but on my conclusions, we are trying to look at some of the health uncertainties, and that may be a major role. And we can do that looking at some of the work by Colin Lee in his paper that came out this year.
Time for maybe one more question. Right, no, then thank Forrest again. And she's going to tell us about APEC flu in North China estimated by the Nestle grid. Jessica Hobbs, please take it away.
Okay, okay.
So they all talked about the pollution in China, and I'm going to talk about those good days. And morning, everyone. I'm Yishen, a PhD student from Professor Hong Liao's group, Chinese Academy of Sciences, and happy to be here to report what we are doing with the high-resolution geoscale model recently with the next few minutes. And my talk today could be simply divided into the following 5 parts. And at first, a word to you. And you may know that people in Beijing have experienced a precious time during last year, APEC period from November 5 to 11, and many things disappear during the winter time as a result of the heavy haze compact to us. And sunshine, the blue sky, the fresh air, just like we have those days in Boston. And here is a photo of Forbidden City during the APEC period. And Chinese people gave those days a good name, APEC Blue, and even took APEC as air pollution eventually controlled instead of its original meaning. And here are the major emission control reductions taken by the Beijing government and during APEC period, including those on traffic restriction, on factories, holidays, and more important, Beijing worked with neighbor to control emissions, and as a result, the emission during APEC period on North China was decreased by 30% on average. And actually, the meteorology conditions were not quite conducive to the transport of the pollutants, especially on especially from November 8 to 11. And here we just show the daily average meteorology data for the GEOS FP. Low wind speed, no precipitation, and stable atmospheric conditions. And to fight against the unfavorable factors, Beijing government began to take the emission control measures from November 3 to which is before the meeting and ended on November 12, so as to ensure the air quality during the whole meeting period. And here I will do the model description and the missions briefly. And we use the quarter resolution nested geoscam model driven by the GEOS FP meteorology field to simulate aerosols in China. And thanks to the hard working of nested working group and the help of Professor Yuxuan Wang, and we make this have this version of geoscam run on our computer. And here is also the domain and H-type emission we used in our simulation, which seem to be the best for us. And with all the things I mentioned above, we want to investigate the impact of emission control and air quality, or we can say the PM 2.5 concentration in Beijing with the unfavorable atmospheric conditions. And here for this talk is just the start, since we just want to use this special period to test the performance of the high resolution geoscam model to simulate aerosols in China. And okay, that's the simulation. For lack of the observations for individual aerosols during APEC period, so here we just use the 2014 Beijing Compact data to test the performance of the model. And the period is from the February 24 to March 12, wintertime coal burning season, which is seen as the APEC period to some extent. And yeah, and in general, the model could capture the daily variation and those peaks of different aerosol species. Sulfate and OC are underestimated, while the BC and nitrate are overestimated, which lead to an underestimation of about 50% of PM 2.5 concentration in Beijing. And all the data show a good relationship, good correlation, and the low bias in the sulfate and nitrate indicate that maybe we should do more to improve the sulfate forming mechanism and the regional emissions of organic carbon in China in the future. And for the APEC case, we conducted 2 numerical experiments and the no control experiment and control experiment. The control experiment was designed according to the EPA's report after the meeting, and you can see details in this picture. Sorry. And same as the normal case, the model captures the daily variation and those peaks in October and November 2040. I'm sorry, this 2040 here. And except for those peaks with high resolution, with high PM 2.5 concentration greater than 200 microgram per cubic meter. And we can also see APEC blue period in this picture. During APEC period, during APEC emission control period, both observed and simulated PM 2.5 concentration were significantly reduced. And the simulated PM 2.5 concentration show reductions of about 58%, while the observed PM 2.5 concentration show reductions of about 57%, and all the data show good correlation. And for individual aerosol species, here during APEC period, the simulated concentrations of the various aerosol species show decreases of 25 to 30% with emission control period relative to those simulated with no emission control. And when we come to the North China domain, we get the same result. Simulated concentrations of PM 2.5 decreased by 43 to 51% during the APEC relative to other days in October and November in 2040. And observed PM 2.5 concentration decreased by 38 to 41% during the APEC period relative to other days in October and November in 2040. And here's the summary, and I prefer not to repeat them again. And in a word, the model do well in reproducing the reductions of PM 2.5 concentration during APEC period relative to other days in October and November 2040. However, with a low bias of about 50%. And maybe we should do more to improve the result, and we will work on this topic in the future. So thanks very much for your attention. Yeah, actually for us, we just get the result on maybe April 20, because it takes us a little bit time to run the high resolution model. And maybe we will do this in the future, yeah.
So in your time series results, when you ran the model with no controls, it was also pretty clean during the APEC period. This is what it looked like. I mean, it was very low compared. So a little bit lucky with the meteorology in terms of the time period?
Yes, it may be so. We will investigate on the maybe effect of the meteorology conditions later on. Yeah. Yes. Yeah, so that's what we want to do.
We'll have Meiji Jia from Tsinghua University, last but not least, and she's going to tell us about the impacts of large-scale circulation patterns on winter haze over China.
Hi, everyone. I am a PhD candidate from Tsinghua University, and my topic today is about large-scale circulation patterns and winter haze over China. We all know that a severe and persistent haze outbroke over eastern China in January 2013. And this is an observed maximum surface PM 2.5 for the haze mass, and we can see the maximum PM exceeded 130 micrograms per cubic meter in more than 20 cities. And to find out the meteorological reasons for the severe haze, we start from analyzing the change of the large-scale circulation patterns of that mass. This is the long-term mean January sea level pressure and wind field, and we can see that the Siberian high is a dominant large-scale circulation pattern in winter over East Asia, and it also causes the prevailing northwesterly winds along the East Asian coast. And this is a sea level pressure difference for January 2013. And we can see that the intensity of the Siberian high is much weaker. And there's also an eastward extension of the Siberian high. Along with this are the anomalous southerly winds over North China. So we want to know whether there's a connection between winter PM and the large-scale circulation pattern on a longer time scale rather than only episodic cases. Since long-term observational PM data in China is not available, we take modest aerosol optical depths to represent the variations of PM in China. This is the mean difference of aerosol optical depths between this time period and this time period. We can see that North China is among the regions with the highest aerosol optical depths increase. So it's not surprising to find an increasing trend in North China mean AOD. Since we think this kind of increasing trend is driven by emissions rather than meteorology, we detrain this time series in the later analysis to just focus on its internal variations. And we get this red line in the plot. We also take the years outside the residual confidence interval to be extremely high and low LD years. First of all, we tried the conventionally used Siberian high index to see whether its center intensity is related to North China AOD or not. However, from this plot, we can see that the two time series seem to be not correlated with each other at all. Then we take a deeper look at the sea level pressure difference between high and low LD years. Of course, we find no significant sea level pressure difference over Siberian region. However, from the sea level pressure difference over Japan and over the region west of the Mongolia, it reminds us maybe the position of the Siberian high is more important in influencing North China AOD. According to this, we define our Siberian high position index using this equation, where L in the equation represents the longitude of the grid within the 123 hectopascal isobar and the definition domain. That's the red box in this plot. And P in the equation represents the sea level pressure of the corresponding grid. And the results show that our Siberian high position index quite captures the internal variance of North China AOD, and it explains almost 60% of the internal variance of North China AOD. And then let's have a look at the simulated SHPI and PM in GeoSCAM. From this plot, we can see a model well captures the internal variations of SHPI, and the correlations between modest North China AOD and model North China surface PM 2.5 in turn testify that we can use AOD to represent PM in China. From the lower two plots, we can see both NSAP and model SHPI quite captures the internal variations of North China PM pollution, and also the most polluted maps both correspond with the highest Siberian high position index. And then we use 30-year NSAP reanalysis to try to find out the mechanisms behind the relations between Siberian high position index and North China AOD. This is a mean difference of wind speed between high and low SHPI years, and we can see in high Siberian high position index years, wind speed on 850 hectopascal show a 13% of decrease, and this decrease of wind speed also exists on other levels like 750 hectopascal, and this is favorable for the accumulation of pollution over North China in high SHPI years. Moreover, the surface relative humidity in high SHPI years over North China show a 12% of increase, and this is favorable for the hygroscopic growth of aerosols. So we think these two factors are the reasons to explain high PM pollution over North China in high SHPI years. And to summarize, we start from analyzing the anomalous large-scale circulation pattern for January 2013, the haze month, and we find an eastward extension of the Siberian high. Thus, we define our Siberian high position index, which explains 58% of the internal variance in North China AOD. Also, some high PM events correspond well with high Siberian high position index, both in observation and in the model simulation. Finally, our analysis about the mechanisms show that the enhanced relative humidity and the suppressed prevailing winds over North China in high SHPI winters are the reasons to explain high PM pollution in high SHPI years. So thank you for your attention.
So just kind
it looks very nice overall. The hydroscopic growth, I mean, usually PM 2.5 should be reported dry. So can it really be the hydroscopic growth contributing to the measure of PM 2.5?
Well, we haven't looked at the observational PM data for high SHPI years. So
The AOD, of course.
yes, we're not sure about that.
Okay. Have you considered the cloud? So for the modest AOD, if there was too much aerosols, they argue with them to assume aerosol was cloud, so remove the seeds. So do you consider this factor, and what's the importance of this factor on your analysis of the trend in AOD?
Well, we also tested mice AOD and find a very good correlation between these two kind of AOD data sets. So,
Yes, please. You.
Well, I just feel like for that January 2028, there's also an increase in emissions during that period of time. Do you have a sense like how much is contributed by the emission increase and how much is contributed to this circulation? Like from a development performance of this really to that severe case.
oh well, actually, we haven't estimated that, but the work done by other members in our group find that if we use the same emission, if we give the same emission of 2013, we also find that we can also find that the surface PM 2.5 for 2013 higher than the previous years if we gave the same emissions.
One last question.
So about the impact growth, the 500 VR ring, it looks like you only show the wind speed map without the direction of the wind. But I think the divergence and the convergence, it might be more important, like transport. Yeah, to impact the transport of this aerosol.
Yes.
So if it's a strong wind, it also can be like divergence. It's not convergence, so it cannot because the haze.
Yes, there's a convergence of water vapor in high SHPI years, and this is can explain the hygroscopic growth of aerosols.
Right. Thanks, Richie, again. And I now ask the presenters to line up, and each of you is going to have half a minute to present your poster. Introduce your poster. Oh, okay. Yeah, after you guys talk, could you please move over to this side so that it would not be too crowded over there. May I also ask each of you to briefly introduce yourself as well.
Yep.
I'm third. All right, first we'll have Evan Kuzo from MIT.
Hi, I'm Evan Kuzo, and we have quantified co-benefits for ozone and PM 2.5, looking at a number of global climate policies in the US, China, and Saudi Arabia. And our future emissions came from MIT's Human Systems Model, which takes account of global economic activity, population growth, and agricultural changes. Thanks.
All right, next we have Aoxin Zhang from Peking University.
Yeah, hi, I'm Aoxin, and I'm an undergraduate student from Peking University, and I work with Mei Fu, who was once a PhD student of Daniel, so I'm kind of an academic grandson of him. And my work will focus on the correlation and relationship between the climate and aerosol. We found the correlation between them in a 5-year time period, and in the past in the past 10 years. And so if you want to know more about the correlation between them, and please drop by at poster C7, and we look forward to your suggestion. Thank you.
Hello, everyone. As we've seen, model PM2.5 to AOD ratios are really important for satellite-derived estimates of surface PM2.5. But how well does GeoSChem simulate this ratio? To help answer this question, we've developed a global network known as Spartan that measures surface PM2.5 mass, composition, and scatter with consistent instrumentation. And we also co-locate our sites with existing sun photometers. This gives us the unique ability to directly evaluate how AOD relates to PM2.5, as well as its chemical constituents on a global scale. Thank you.
And Jan from Peking University. Next. Yep, Hong Yan from Tsinghua University.
Product also redistribute regional consumption-related pollution impact in our study develop a linkage between the economic multi-region input-output table and the GC adjunct model. This framework can be used to attribute regions pollution impact to different regions according to their consumption related consumption, include the products import and the product produced locally. Detailed information can be found in my poster.
Next, Junmei Xu from WC.
If you'd like to know more about geostationary satellite and how we can use it in air quality studies, then come check out my work on estimating PM2.5 in China using a new geostationary satellite instrument called GOSI, combined with simulations from GeoSChem. Given the high degree of consistency between our estimates of PM2.5 and hundreds of ground measurement stations, we further interpret the chemical composition of PM2.5 in China using GeoSChem. Thanks.
Research Institute of Japan.
Hi, we experienced a 7-day rusting air pollution in the west part of Japan. This long rusting air pollution is caused by the trapping and the broke the high pressure system. During the event, we compared the model result with the various observations, including POPC, radar, and some chemical composition. And we also performed the source receptor analysis to quantify the impact of the emission sources. Thank you.
Next, we have Luke Reed from CU Boulder.
Hey everyone, I just want to pose a couple questions with regard to the transboundary transport of PM2.5 in the Western Hemisphere, and hopefully pique your interest and have you come talk to me about it, where all the information is on the poster. So really, if you're interested in finding out what ability each region or nation in the Western Hemisphere has to control their own PM2.5 levels, the associated emissions with regards to sectors and species, and how we can use an adjoint to create this emissions 3D Jacobian of sensitivities, come talk to me and find out more.
Next, we'll have Ming-Wei Li from MIT.
Hi everyone, in this project we quantify the effects of changes in Chinese exoplanet emissions on the inorganic PM2.5 over both China and the US. Besides the best guess scenario, we also investigate the sensitivity of the PM2.5 to its precursor emissions. So if you're interested, please come and talk to me at my poster. Thank you.
Next, we have Yi Kang from CU Boulder.
Hello everyone, I'm Ping Kang from CU Boulder David Hansen's group. Our research is mainly focused on using GeoSChem listed model to output PM2.5 distribution and composition information in China. We also use the observation data to validate our modeling results. So we have found a lot of interesting results. Like that, we found that GeoSChem will overestimate it in the rural urbans, but underestimated in the urban rurals. So for another more details, please come to see our poster. Thank you.
So it's well understood that temperature is an important driver of tropospheric ozone pollution, but it turns out these impacts are non-uniform across the ozone distribution in the observations. How well does GeoSChem reproduce these differences in quantile sensitivities? Do they matter? And perhaps most importantly, how do they compare to other popular name brand models? If you're curious about these questions, please drop by. See me at 4 o'clock. Thank you.
So this poster will represent the global estimate of CO and NOx emissions using the multiple species data simulation. So by means of multiple data simulation in the regular GeoSCAM adjoint cycle, instead of using only one observation operator, we began to use multiple observation operators together, including CO, test ozone, OMI, NO2, and formaldehyde together. So if any one of you are interested in how the posterior looks like and also the tracer's concentration, please look at C17. Thank you.
Hello everyone, my name is Yaping Ma from Peking University. My work focuses on trend and variability of one-time visibility in the north-south plane. The method used for analyzing the visibility is shown on the right, and the results can be divided into two groups. If you want to know more, welcome to the front of my poster. Thanks.
Hello, this poster is about the plan to develop the UTX adjoint and apply it to assess the environmental impacts, mostly ozone depletion impacts from supersonic aircraft that fly within the stratosphere.
So my poster is on parameterizing the near source chemistry of biomass burning smoke plumes. We use the aerosol simulation program, which models organic aerosols. It can be used in Eulerian 3D models or Lagrangian models. So if you're interested in biomass burning parameterization for your global model, come see my poster C20. Thanks.
Right, and finally, we have Shannon Hopkins again from Harvard.
Hi, don't worry, I'm the last one. So I'm again working with Loretta and Danielle. And so typically when we think about fires in Indonesia, we think El Nino, but Singapore experienced its worst pollution on record in June 2013, and it was not an El Nino. And we think something similar happened in August 2005 in Kuala Lumpur. So we think we've identified an unaccounted for meteorological pathway for smoke exposure in the Malay Peninsula. And we also think that MODIS AOD may have some trouble detecting these haze events, but OMI AI does a decent job. So please stop by.
Right, so that concludes our section, and
no special announcement. We reconvene at 10 after 1. Please be prompt. Have a good lunch. Hold it like a rap. Hold it like a rap.
I'm better at dancing than oh yeah, I am good at dancing. Hello. Can you hear me? Like this is good. This is good. Can I hear myself? I can. Okay, one, two.
Just to see how it sounds, I think it's to stand like back there, kind of where that guy is sitting.
Yeah.
And kind of test it out, and then you can hear, because that up here sometimes it's hard to tell what you're hearing.
One,
but
two,
there you
one.
can see how it sounds.
Oh.
Oh yeah, of course. I just want to make sure you can see it on where it's going to be presented. Oh.
1, 2, 1. Is it on? I don't even hear myself. Sorry. Oh,
It should be.
It's
you want to flip through it?
Yeah.
Testing, testing. And so if you're talking about like this, it's picking it up, but it's not. If you do this, then you get kind of it gets intense.
If I do this, so it's not good. Okay. Like this is okay? This is true. This is not too close. Yeah, okay. I would think it's my accent.
Sure thing. Yeah, we've got them here. You were very convincing.
Okay. Okay, so surface, ozone, vegetation, and geoschema adjoint. And this first picture is these two pictures I took last summer in Rocky Mountain National Park, the one on the left. And this is a natural plant that grows there. And when there are these high levels of ozone that are very common, it produces these black spots. So it's ozone damage. The picture on the left is from our educational ozone garden in Boulder. And it also shows, this is especially sensitive, ozone-sensitive variety of snap beans. And that's you can see what happens to some ozone-sensitive crops. So ozone, surface ozone, is the most damaging air pollutant for vegetation. And why we care about it? Because first of all, it reduces production of biomass, and biomass is our source of food. So previous studies did a really nice job analyzing effects for present and future crop yields, effects of surface ozone. And also at least one study that we are aware of also analyzed long-range transport effects on crop production in the Northern Hemisphere. So the focus on this work is analyzing sources that lead to biomass reduction due to ozone in the United States. And I will be looking at these four plants. So ponderosa pine, aspen, wheat, and soy. And I picked them because they're all very ozone sensitive. There's 2 trees and 2 crops. And this is pretty established methods how to calculate reduction in biomass or in crops. First, you need to know where stuff is growing, then when it is growing, so what is the ozone exposure during this time period. And then you take empirically obtained exposure-response relationship from literature, and you can calculate what was the fraction lost. And this is an example of this. So this is one of the metrics that is used for this analysis. There are at least 3 of them, but W126 is the one that applies differential weighting to daytime ozone concentrations. And you can see as ozone exposure goes up, this is the fraction of crops or biomass growth reduction that takes place. So like up to 40% in this case. And so these are the estimates of these 3 metrics during the growing season for wheat. So this analysis for wheat, this is just forward nested simulation. And these are 3 metrics. As you can see, they're all slightly different. And what I would like to say that we adjusted daytime ozone concentration to canopy height. So model outputs concentration in the midpoint of the lowest layer. And because of the presence of deposition flux near surface, actually ozone concentrations at 1 meter, that's what we are concerned with here, they will be a little bit lower. That doesn't have a huge effect on mean concentrations, but it will affect our metrics a lot when we have either differential weighting or threshold of 40 ppb. That is what AUT 40 is doing here. So after we applied this, accounted for gradient, we actually improved agreement with observation, but some bias remains. So we also created these correctional factors to account for this bias, to get the best estimate of the exposure. And because for wheat, we have 3 different response relationships, we work with the mean of these 3. And so in each grid cell here, it's shown how much wheat would be reduced due to ozone exposure during this time period. And now to obtain national aggregated % loss in biomass or crops, we multiply by the density of crop production or density of trees that grow there. And then we can figure out that, okay, 3%, between 2 and 3%, that's how much ozone-induced loss in aspen or ponderosa pine happened in this year. And we have 3 different relationships for wheat and soy. So I would like to point out that in this case, when we aggregate over a nation, it's actually a pretty good agreement between a coarse and nested simulation. And now we move to adjoint results. So adjoint is wonderful because you can get spatially resolved sensitivity to model parameters. And in this case, I'm concerned with emissions. So this shows sensitivity to global North American anthropogenic emissions. And all it shows that like crop wheat in the US is much more sensitive to nitrogen oxides emitted from US than from anywhere else. So this is kind of obvious. So US contributes most of this influence on our function. However, for carbon monoxide, actually Chinese emissions suddenly become very important, as expected. And actually for ponderosa pine, we found that contribution of Chinese CO was higher than contribution of domestic CO. So we can repeat also adjoint analysis on a nested domain. So to easily interpret the results, I aggregated them by state. So what it shows here, it's again for wheat, and it just shows where most wheat grows. And this shows where most of wheat loss will take place. So the high spot is where it grows and where ozone concentrations were high. And then this just shows state share of nitrogen oxides emissions that are most important for this. Now, when we move to a joint result, this is actually shows how much these emissions of nitrogen oxides contribute to our wheat loss in this case. So we see that even though most of wheat is lost in Kansas, most of emissions that impact this loss are coming from Texas. So Texas is a very red state in this case. So then we also can compare the share of contribution of NOx emissions to actual share of emissions. And we see that Texas, again, is red because it contributes more than its fair share of emissions to wheat loss. And another result here shows actually that Texas, again, is disproportionately, so the wheat loss that Texas suffers is quite lower than contribution of NOx emissions that Texas imposes for national wheat loss. And now we'll leave you with conclusions here and see if there are any questions.
Perfect timing. We have 3 minutes.
Is there a time period of the plant's growing cycle that's more susceptible to ozone? And would that be something you could incorporate?
Yeah, so I was talking to EPA scientists about that, and they said just take any maximum 3 months season for ozone. So in this case, for trees, I'm looking at May, June, July, or it could be June, July, August, which will be slightly different. But yeah, probably it depends on specific tree and maybe location. So these small ecological effects, I don't take into account. But for W126, they're always concerned just with the highest value of ozone.
Jenny?
I'm surprised your effect from CO is so large. It's almost as large as for NOx.
Yeah, I didn't mention it. So these results are normalized to total. So CO anthropogenic is like around 14 times lower than NOx anthropogenic. Yeah, it's just different plots that I didn't show here.
Does some of that influence, the kind of stuff you showed for Texas also hold true for some of the other crops?
Yeah, so I was looking only 2 crops, and I just started analyzing these results. So yes, there is also interstate transport. Yeah. So the main conclusion is that influence is not always proportionate to emissions. Definitely, yeah.
Well, thank you very much. Our next talk is by Stephen Barrett, Aviation's Impact on Atmospheric Composition.
So one of the interesting things about aviation is it's really a unique source, being the only anthropogenic source today that occurs in the upper troposphere and lower stratosphere. About 2/3 of the emissions from aviation occur in the upper troposphere, about 1/3 in the lower stratosphere. Now, future aircraft we might be interested in designing, including supersonic aircraft and also very efficient aircraft, are likely to fly well into the stratosphere. So all of this means that to assess the impacts of aviation on atmospheric composition, we're using geochem. We need a comprehensive treatment of stratospheric chemistry in geochem. Now, fortunately, I was very lucky in that I got 4 years ago an extremely smart PhD student, Seb Easton, who just graduated on a Wednesday, and he was able to solve this problem by implementing something called the Geochem Unified Chemistry Extension that adds full treatment of stratospheric chemistry to geochem. So I'm going to talk about that and also an application to aviation. First, the Geochem Unified Chemistry Extension. Now, if we start with the base version of geochem before this UCX edition, it's had the following treatments you can see here for different components of the model. In the stratosphere, however, almost everything was relaxed to a climatology, which is perfectly appropriate for tropospheric focused studies. But in the case of aviation, it means that quite a lot of the impacts got wiped out, especially in the stratosphere. And also, it didn't have some of the physics necessary to represent processes that we care about. The UCX includes now online water vapor. So aircraft actually emit water vapor that matters in the stratosphere, where it can promote ozone depletion. Also, online methane. Aviation contributes to methane depletion and also then water reduction in the stratosphere. We have online treatment of stratospheric aerosols, which less relevant directly to aviation, but is a good way then of diagnosing the performance of the model by assessing stratospheric ozone hole formation. Then we have a full unified chemical scheme through the troposphere and stratosphere that was based on taking GMI's chemical mechanism, merging that with Geoschem, and evaluating it to check that they didn't screw up the existing tropospheric chemistry. And then also some heterogeneous chemistry, and the new FastJ X 7.0A from Prather's group has been implemented in Geoschem. Now, probably the most interesting way of evaluating the performance is to look at Antarctic ozone hole formation. Here are measurements from TOMS. You can see here south to north pole over 4 years, and the yellow patches at the bottom are the ozone hole forming and collapsing. The base version of Geoschem didn't get these holes here. You can see the big hole here is missed, and then the UCX version does capture these holes both in the depth and the extent of the formation and collapse of the ozone hole. Another way to view this is compared to ozone sonde measurements. Here you can see ozone sonde measurements with crosses, the base version of Geoschem in yellow, and the new version, SEBS version, UCX in light blue. And you can see we capture between 80 and 90% of ozone hole depletion. Some reasons that we don't get all of it is because we probably don't quite resolve the polar vortex, so there's some diffusion of material to and from the poles, and probably other reasons too. This was published last year in Atmospheric Environment, and now the Unified Chemistry Extension is in the standard Geoschem release, which means that anyone interested could study the effects on the stratosphere of processes they might be interested in. So I think I'm actually on time, remarkably. Okay. So now I'm going to talk about application to aviation. Now, aviation emissions occur almost entirely in the northern hemisphere. There's really nothing in the southern hemisphere today, and they are focused particularly in North America, in Europe, and growing in Asia. If we plot this quantitatively by longitude, you can see here the extent of dominance of North American aviation here. This is the US East Coast. And then European emissions too are significant. Now, if you look at the colors, you'll see yellow is the year 2000, the salmon color is 2013. North America and Europe aren't growing very strongly, but in Asia, you can see more than a doubling in fuel burn and emissions from aviation over the last 10 or 15 years. So a remarkable growth rate in Asia. And that's actually driven this growth rate in aviation fuel burn and emissions over the last 15 years, some calculations by Luis Alvarez at MIT. And if you go back to 1990, from 1990 to 2005, aviation more than doubled in emissions. And from now until 2050, we expect a tripling or more of emissions. So it's going from a sector that's really quite small to something that over time will become dominant for countries that are reducing their emissions. So currently, Geoschem has emissions for 2005 for aviation, which was a recent update to the old 1990 emissions that were less than half. We're now working on a 1990 to 2014 time series of emissions to enable historical analysis, particularly important if you're doing anything in the past where the aviation emissions are less than half what they are now. Putting this into Geoschem, we find aviation causes up to 6 ppb of ozone formation in the upper troposphere in northern latitudes. It then destroys ozone in the stratosphere up to -4 ppb. So this is just emissions really occurring at about 11 kilometers typically in this region here. So clearly some of the effects do diffuse into the stratosphere, and that's something that really wasn't known before SEB's model. On the surface level, you can see impacts propagating down to the surface, about a 2 ppb perturbation at the max. That might double or triple by mid-century. And it's also increasing the ozone column on net by 0.5%. So if we think about the implications for humans of all of this, previously we studied particulate matter from aviation that caused about 9,000 deaths a year. Ozone is produced very efficiently by aviation. We find that causes about another 7,000 deaths per year. So that means that aviation is pretty unusual in that ozone relative to PM in terms of the health burden is actually very important, whereas for most sectors, ozone is really a secondary issue. And also the UV reduction at low altitudes results in about 400 fatal skin cancers, that reduction of 400 fatal skin cancers per year. So I finished what I make as 31 seconds early. Thanks. Which I'll redirect to Seb, basically. Why didn't you come here? You did all the work. Yeah.
I was just going to ask, along with the trend in sort of aviation traffic, is there a significant trend in the emissions from each aircraft?
Yeah, so the trend is probably negative. So if you want to reduce aviation fuel burn, which is sort of the economic thing that drives technology development, and you want to reduce CO2 emissions, you want to have higher combustion temperatures. Higher combustion temperatures, which is second law, right? Higher max to min temperature gives you a maximum Carnot or higher Carnot efficiency. But higher combustion temperatures give you more NOx emissions, and so NOx emissions per unit fuel burn have been increasing over time. So it's sort of a strange situation where things are actually getting worse.
Given the sign change across the tropopods, how sensitive are your results to resolving that dynamical tropopod such as folds?
What do you think?
Thank you. I think that resolution of the dynamic tropopods is important. So one thing I would point out is with the implementation of the UCX, it's unified. So we don't rely on a specific cutoff from the meteorology, but suddenly what the meteorology does in that region becomes more and more important. So yeah, I think that resolution of that is going to be important. I would like to see some work on, in fact, the general impact of vertical mixing on aviation's impacts. You saw that there's 1 to 2 parts per billion of ozone coming to the surface. That could change a lot if there's overestimated vertical mixing in the presence of aviation in the free troposphere, for example. I hope that answers your question.
My question is kind of related to the last one. So I noticed that you use the online water vapor above the troposphere and use the fixed water vapor under the troposphere. So would that be a problem at the boundary?
Okay.
You go first.
So at the boundary, I mean, it's consistent because the offline water vapor is taken from meteorology. So that's consistent with the geochem treatment as it is. At the boundary, what happens is that whatever is present in the troposphere is essentially used as a boundary condition for the stratosphere. In the tropics, that's going to result in a source, and outside the tropics, that's going to result in a sink. And I don't think there's a serious inconsistency there. One possible inconsistency actually comes from the definition of the tropopause, because that is the one point where the definition of the tropopause is important, the separation for water. We're actually working on addressing that by having a different boundary condition where rather than using the dynamic tropopause as predicted by the model, we instead use the cold point and specify a water vapor mixing ratio, and that should make it a lot less sensitive.
You were talking about the trend of future emissions. Are planes in the future going to fly higher and more in the stratosphere?
You don't want this one.
I really don't.
Well, it's quite likely. So you basically want to fly as high as you can for the thinnest air density. So if you go back to the 1970s, planes, or well, say aircraft designed in the 1960s, cruised about 23,000 feet. That's 6 kilometers, I guess. Now they're cruising at 11 kilometers. Future ones maybe 12, 13 kilometers. And the thing that limits the altitude is the lightness of the structure of the plane. So aircraft are getting lighter. And once you get lighter, you want to cruise higher for thinner air. But you can only do that to the extent you can build a light enough structure to have a big enough wing to produce enough lift in the thinner air as you go higher and higher. So provided we continue to see improvements in the structures of aircraft, then you would expect them to fly higher to have lower fuel burn. Now that would also make a lot of environmental sense because the ozone production efficiency peaks almost exactly where aircraft fly today. So that's sort of historical bad luck. And the ozone warming from aviation is about the same as the CO2 warming. The other thing is that contrails from aviation, these are line-shaped clouds, cause about as much warming from aviation as CO2 as well from all historical emissions. And if you take the sort of PDF of the space-time supersaturation in the atmosphere with respect to ice, which is what you need for contrails to form, that supersaturation peaks at exactly cruise altitude today. So we've sort of, by bad luck, chosen the worst possible altitude to have aircraft fly at. And if we could make them fly above this ozone production peak and contrail peak, then we would be in much better shape.
We should I should just let you know, for your CV, we're going to give you a credit of 0.5 to 0.75 for this talk.
Oh, I see. Okay, thanks. I'd say it's more like 0.1 actually in terms of work.
Our next talk is by Kelly Wells, simulation of nitrous oxide sources and sinks with geochem and the joint evaluation of observation.
All right, good afternoon, everybody. I'm Kelly Wells from the University of Minnesota, and I'm going to be talking for the next few minutes about N2O. So, of course, N2O is a greenhouse gas, and it is emitted at the surface and lost in the stratosphere. It's quite long-lived, with a lifetime of about 120 to 130 years. So it's quite well mixed in the troposphere with a mixing ratio of around 325 parts per billion. The primary contribution to the N2O burden in the atmosphere are emissions from soils, both agricultural and natural soils, where N2O is produced via microbial denitrification and nitrification. And we've been observing a growth rate of N2O of about 0.8 ppb per year, and that's thought to be due primarily to the increasing use of nitrogen fertilizers. So we've collected observations of N2O from April of 2010 to April of 2012 and used them in an inversion framework with the GeoSchem adjoint to answer the following two questions. The first, how well do different observations of N2O constrain their emissions and sink, and at what time and space resolution? And second, where are additional measurements needed to get better observational constraints on N2O emissions? So we use these different observations in an inversion to solve for emissions at 4x5 degrees resolution, as well as stratospheric loss frequencies, which we aggregate to 8 equal latitude bands. And for the sake of time today, I'm just going to focus on the results pertaining to the emissions. And here we have our different observational data sets. We have a number of surface sites here. The bulk of these are weekly FLASK observations, but we also have a number of sites where there are quasi-continuous measurements from which we use hourly averages. We also have a number of flights from Karibik, which is an instrument container on a commercial Lufthansa aircraft. And most of these observations are FLASK observations taken at cruising altitude of the aircraft. And then finally, we have 3 of the 5 HIPPO campaigns occurring during our study period. These include pole-to-pole sampling of N2O, quasi-continuous measurements with a number of vertical profiles as well. So to evaluate how these different types of observations give us constraints on N2O emissions, we performed a number of observing system simulation experiments, or OSSEs. And this is done simply by sampling your model at the time and location of your observations, and then inputting those into your inversion, starting with a perturbed initial state. In our case, this is for emissions, and then try to see how well those observations get you back to the true model state, which in our case is a scaling factor of 1. So just to show some example results for emissions, on the lower left here, this is the zonally integrated N2O emissions in terms of teragrams of nitrogen per year. The true model emissions are shown as a black line, and then we start with an initial a priori guess of 0.5, scaling those emissions down uniformly everywhere. So that's the red line. And then the solution for emissions achieved using surface data is shown in green, HIPPO is in orange, and then with Karibik data for blue. So you can see that both the surface and the HIPPO data give a good recovery of that zonal distribution of N2O emissions, whereas the Karibik somewhat less so. And in any case where we apply a uniform bias in our initial conditions, the surface and the HIPPO data give a good recovery of the true model emissions. However, if we apply a seasonally or spatially varying bias, that's not necessarily the case. So with the help of Nicolas Bousseret at CU Boulder, we've been looking at a couple of different diagnostics to try to get a more realistic picture of what are the spatial resolution of our constraints. So what's shown here is the reduction in the emission uncertainty that we get from an approximation of the inverse Hessian. On the left are the results for using surface observations. And so we can see that kind of these red spots that pop out in the results are locations where we have continuous monitors, so we get quite good error reduction in the vicinity of those locations, and also upwind of Europe and in North America we have a fairly dense sampling network. From the HIPPO observations, we get pretty good reduction of emissions over the central US where there are some flights, and then some reduction in emission uncertainty in East Asia, which is kind of a large source that's upwind from our flight tracks in the Pacific. So, but you can notice from both of these observations that we have just these large areas of white in the tropics and in the southern hemisphere, indicating a lack of spatial constraints in those regions. So we also calculated the averaging kernel for the inversion for 3 different types of locations: and a site with hourly observations, weekly observations, and then a remote site with no nearby observations. And in this case, the degree to which the averaging kernel in your location is close to 1 and is 0 elsewhere tells you how well you're resolving those emissions relative to the emissions in surrounding regions. So at our Tall Tower site in Minnesota, we have hourly observations. We get quite good. We resolve the emissions in this grid box quite well. Once we get to Flask observations, this is for a site in Hungary. We have a weaker averaging kernel value and we start to get some smearing. But once you get to that remote site, you have very weak values. The averaging kernel is very highly smeared. So we have very weak constraints in this region. And we also, you can see we can kind of risk conflating emissions in the tropics with those in the extratropics. So this has implications for your inversion results when you're optimizing for that source. And then lastly, just in terms of starting to look at where we might need additional observations of N2O to get more constraints on the spatial variability of emissions, we applied our the reduction in our emission uncertainty to the emissions in our forward model, just scaling by 1 minus that emission reduction, and then ran the forward model for a couple of months. Here is an example shown here for August and September of 2010. And then you can see several ppb above the background of this unconstrained N2O that is being emitted in the tropics. So we really could use some additional observations in these, particularly kind of these continental outflow areas. Additionally, by the second month of the simulation, you can see we get quite a good lofting of emissions throughout the troposphere in the tropics. So we could benefit from additional aircraft observations in this region as well. So thanks. Yeah, Daniel.
So I understand that soil pulsing is a major source of N2O.
Mhm.
And are you capturing this, and to what extent would it affect an observational strategy?
We're not capturing this. So right now our a priori is basically just temporally constant. We don't have any variability. But we see that, like, for example, in the observations of the Tall Tower site in Minnesota, it's quite close to a lot of agricultural fields, and you do get very strong pulsing, you know, kind of right around the snow melt time, where I think those N2O is kind of built up in the soil, and then when it thaws, you get these pulsing, and then obviously you get pulses once fertilizer is applied as well, and then after rainfall events. So yeah, there's a lot of complexity in terms of the meteorology.
That would help detectability.
Yeah, definitely.
I had a quick question. I thought I understood you were also adjusting stratospheric loss frequencies.
Yes.
How do you deal with the spin-up issue?
So we actually constructed initial conditions based on observations. So in this, in the troposphere, we used the surface Flask observations to kind of construct initial conditions. In the stratosphere, we used MLS data, so retrievals, and those are from about 100 HPA up. So, and then we kind of just linearly interpolated in between. But I can say that just at least looking a bit at the comparison to the aircraft data, there's definitely an underestimate of some of those kind of upper troposphere, lower stratosphere mixing ratios.
Thank you.
Yep.
We'll move on. Our next talk is by the new multi-scale framework for atmospheric source inversion in high-dimensional. We changed the title. We'll let it go. Completely different. I think there's a couple of words.
It's related, Steve. So I have to use that? Or yes. Can you hear me?
Yes.
Yeah. Okay. Hi, everybody. So my name is Nicolas. I'm working at CU Boulder with David Henze. And today I'm going to present a new method for dimension reduction for large-scale inverse problem. So let me introduce the ideas and concept with some simple analogy. So let's consider the following inverse problem. You want to identify each of those faces on this picture. And so some prior information is available. You know, this is Jacob's group picture. So it helps a little bit, but you might need more information to actually identify those faces to inverse the problem. So we are lucky we have a few observations in the form of partially deblurred faces. So you can identify glasses, a beard, long hair. And so if you combine both information and after a bit of thinking, you may come up with a better posterior information. Right? So you can even recognize maybe some of those faces with some uncertainty. So you basically, in some sense, you did a Bayesian inversion. And one important remark here is that quite naturally you focus your attention only on those faces which were partially deblurred, so where you had actually information from the observation. So you basically did a dimension reduction of your inverse problem. Mathematically, when we consider Gaussian error and linear problem, we are looking at the optimal combination, linear combination of the prior and of the model data mismatch. And so we use an optimal, which is called the gain matrix, which can be extremely large, so large that in fact sometimes you cannot even represent explicitly this matrix in your computer memory. So why dimension reduction? Dimension reduction is useful because it allows you to basically directly compute an analytical solution in an efficient way. From a theoretical point of view, you can regularize your problems, which means you filter out the noise. And it gives you also insight. So for the interpretation of your results, it gives you insight into the information content of the inversion. So now what criteria can we use to do that? So for a given dimension, you want to minimize your posterior error, usually. And also another criteria is to maximize the information you extract from your observational system. And so, okay. So there have been several attempts to solve this problem. I will give 3 examples. So the transcom region aggregation, this method consists in partitioning the globe in several domains using some geographically based criteria. And it allows you to do global inversions. But it is highly suboptimal because you don't do any optimization with respect to the information content of your observational system. Recently, Mark Bokeh, 2011, wrote an important paper where he's basically presenting an optimal way to aggregate high resolution grid and to optimize the minimum, so the posterior error and the degrees of freedom for signal. The problem is that you need the Jacobian of your system, which means that you need a small system so that you're able to optimize the grid and then to do the actual optimization on the grid. Yeah. So it doesn't scale very well, and it has been applying to mesoscale inversion so far only. Recently, Alex Turner and Daniel submitted a very interesting paper where they use a clustering approach with very sophisticated radial basis function. They define their basis function based on some prior information. And so in principle, this could be used. The improvements compared to the bokeh approach is that you can actually work with high-dimensional system. The problem is that it doesn't scale well because it's a sequential algorithm when you add progressively element to your state vector, and then you recompute the posterior, and once you reach the minimum, you stop. Also, for theoretical reasons, it's also not optimal because you restrict yourself to a particular class of representation. And so at CU Boulder, we have been focusing on this problem recently. And the good news is that we came up with an optimal and simple formulation for the solution of the problem. And so yes, it works. you just need to trust me, I think, at this point. Okay, so the new approach, minimize the posterior error, maximize the DOF, what we are looking for, and among all possible reduction methods for a given dimension. It's highly parallelizable, which means that in practice it works for high-dimensional problem. Yeah, so just a quick example. We did a 1-month meson source inversion using GOSAT. On the left, you have the constraint at grid scale provided by the observation. So we know that we can independently constrain 400 pieces of information, okay? But we don't know what they are. So with this system, you can actually, here I'm showing 4 patterns that you can fully independently constrain. And so it allows you to disentangle the information content of your inversion and also, of course, to speed up your inversion. And so with that, I will take any questions.
So Nicola, you focused on the original 3 on the role of the relationship between the spatial distribution and some smaller subspace for representation of that distribution. The other axis is equally important, that is the role of time. The role of time. In other words, time itself can be very repetitive and have a lot of correlations. It could also be reduced. In this case, being linear trend. So to what extent do you see this new approach coming soon? Presumably one of the equation 5 in the page.
6 actually.
Yeah, that one. That would, how well do you think that could be expanded to that? The approach that you have coming could be expanded to time part of the problem.
It's directly, you can directly extend it to the time dimension. There is no restriction. It's just a coding problem, basically. I mean, we just need to do that. And yeah, so.
I have another question. Did you have to calculate the full Jacobian for this?
No. It works for.
How did you get it? How did you come up with the dots?
With the DOF?
Yeah.
Well, it's calculated actually. You get the DOF, but it's done simultaneously as a byproduct, basically, of the algorithm.
But you don't have to calculate for Jacobian.
No, you don't. We can talk a bit more about it. Yeah.
So you start going to different representations.
Yeah.
We potentially start moving away from the case where Gaussian errors are actually representative of the system.
Uh-huh.
Have you thought about looking at non-Gaussian errors and sort of interest in that case? Something like dots and valid.
So this is valid for linear model and Gaussian error, but it can be extended. We have idea to extend that actually to nonlinear cases. That's what is interesting, because as soon as you have a small dimension, you can deal with nonlinear problem. That's much easier. So that's one of the ideas. We need first to fix the linear problem, and then we can move away from that. Yeah.
So Daniel sent us all the group photograph yesterday. Nicola is going to send us the photograph with the labels soon, right? Send us the group photograph.
Just to the steering committee.
Oh,
I was not allowed to send such a big attachment.
But he will label all of them.
We'll take care of that.
Yes.
Okay.
So the next talk is weak constraint 4D-OR in CO emission estimation by Martin Keller.
tip to hold it about here.
Sorry?
Just a tip to hold it about here.
Okay. 1, 2, 1, 2. Hello? All right, okay. Hello, I'm going to be talking about weak constraint 40var in this talk. And for those of you who aren't familiar with what weak constraint 40 is, the basic motivation is that in assimilation schemes like 40var, there is a tacit assumption that the transport model that you use is perfect, i.e. that it is free of any systematic errors. And the problem that we're facing there is that that's not the best assumption to make, and that we know that pretty much every transport model under the sun exhibits some form of bias or error. So, okay. So the approach that I took called weak constraint 40var consists in taking the forecast equation with your transport model M and adding a forcing term to that forecast model that can hopefully capture or correct some of the systematic errors. And in the cost function for the inverse problem J here, we also add a term that is proportional to the forcing terms U here and a covariance matrix Q. So in weak constraint 40var, what essentially happens is that we use the information coming from the observations not only to get a better estimate of the parameters that we are hoping to improve, like for example fluxes or initial conditions of some kinds, but we're also using the information to estimate the forcing terms needed to correct the model. And right now that's implemented in the CO only and in the full chemistry version of GeoSChem. Just to show you an example of some of the work that I did. When I first started this out, I was facing the problem that this is a relatively new technique and there wasn't really much information to guide me in the process. So what I did was I did an Aussie where I produced synthetic retrievals of CO profiles from MAPIT using CO concentration simulated using GEOS4 MET fields. And I assimilated these observations using GEOS5 MET fields. So I essentially assimilated observations with a biased model, so to speak. So the difference between GEOS and GEOS5 was used as a proxy of transport error. And for the covariance matrix Q that I showed before that limits the penalty associated with the forcing terms, that shows a particularly simple parameterization, which is just a scalar term multiplied with the identity matrix. This isn't necessarily the best parameterization of Q or even a good one, but it is an easy one that you can easily understand. And for the emissions, I used the same emission data sets as the prior and as the forcing for the synthetic retrieval. So the true emissions over a couple of regions, say for example Africa, are shown up here, which for the particular time period was about 110 teragram per year. The prior was scaled up by 50% to be quite high. And then I'm interested in how well can I recover the true value here from the observations using a biased model in strong constraint 40var, which is just the basic 40var, and then different implementations of the weak constraint 40var system. So when I don't take into account that the transport model that I use is biased, the estimate that I get is quite off. And then different implementations of weak constraint 40var successively get better as the value sigma q here increases. That is, the penalty associated with estimating forcing terms becomes more lax. But as it goes too lax, the terms actually begin to revert to the a priori estimate. And what's happening here is that for a very tight penalty, the penalty associated with correcting the transport model errors is too high, and you effectively just revert to strong constraint 40var. But as the penalty gets too lax, you essentially fit the observations using only the forcing terms, and you don't end up constraining the estimated sources at all. It's also interesting to note that the value where you are closest to the true emissions of sigma q depends on which particular region you're interested in. So that goes to show that the size of the transport error and the particular parameterization that a decent weak constraint system should use depends quite a bit on where you are and what kind of dynamics you're dealing with. To show you some of the estimated forcing terms, I'm plotting here the estimate terms over equatorial Africa and over Indonesia. And the solid black curve is for the least penalty case, and the blue curve is the intermediate case, and the red curve is the one with the highest penalty. So as you would expect, the red curve is very close to a zero, meaning that you don't actually estimate any forcing terms and only use the observation to update the emissions. The blue curve is a little bit larger, and then the black curve is quite big, which makes sense based on what I said before. So you can see that the design of Q and the overall value of Q, or any kind of measure of the amplitude there, that impacts how large the forcing terms are going to be. The other interesting thing is here is that the structure is quite similar, even though these are very different regions, which is somewhat curious. So to figure out what was going on here, I produced a different set of retrievals where the averaging kernels were assumed to be equal to the identity matrix. So I would have perfect vertical sensitivity. And in that case, you can see that the structure is quite different between these two forcing terms here. So that shows that the reason why these two look so similar is that the vertical resolution of the observation that I was using wasn't good enough to actually permit me to see what exactly is going wrong over these two regions. So I think I'll just leave it at that, put summaries up, and I'll take any questions now. Yeah.
How do you determine the sigma Q?
I just played around with it, and I guessed I was exploring how the system responds to different values and then I just picked the ones that were most illustrative that sort of showcase the behavior of the weak constraint system. This isn't in any way something that you should use in a real inversion or in any sort of serious effort, but it was just to study how the estimation of the forcing terms depends on how you parameterize Q. Yes.
So the recent move that Steve Possum mentioned towards the move towards 3 ensemble and 40 ensemble methods within GMAO seems like it would provide an excellent opportunity to provide a more realistic distribution of stochastic forcing terms that you
Yes.
the weakly constrained.
Yes.
Have you considered how that kind of, so if you had the formal structure for that, how that would fit explicitly within the weakly constrained 40-bar system?
I think it's a really interesting idea, but I haven't sat down to actually flesh out something that could be implemented yet.
Question. In your
Yeah.
design of your synthetic experiments, you
Yeah.
uniformly increased the prior over all sources.
Yes, I did.
And you got kind of a consistent sigma that worked the best.
A consistent sigma?
0.1.
Oh, you mean in these cases here?
If
Yes.
you had changed the prior randomly in different regions, would it still give you a consistent?
See, that's actually a thing that I looked at recently. So it would be interesting to see if there's some kind of correlation between the size of the emissions and the forcing terms that you get. I think that's what you're going for, right? Interestingly enough, that's not the case. And I was very surprised by that. That's something that I've only done a few weeks ago, and I'm still not entirely sure what's going on there, but it doesn't seem to be so. I don't know why.
Thank you. Okay, we'll move on to the last forum block of the session. Source sector and regional contributions to concentration, direct rating, and forcing of black carbon in China. Colleague from.
Okay, I'm the last speaker, but it's my first time to Boston. I'm from Chinese Academy of Sciences. I'm now a PhD student in the research group of Professor Hong Liang. And black carbon has significant warming effects and harmful effects on human health. High emission of black carbon in China therefore make these two issues especially outstanding in recent years. So our scientific question is to quantify the contributions from the major emission sector in China and non-China emissions. And here we list the recent emission inventory of black carbon in China. The total amount of these emissions in this inventory is comparable with each other In this study, we use the latest emission inventory H type. The introduction of this inventory emission inventory you can find in ACPD. And in this inventory, you can find the emission from industry and the residential sector together account for almost 80% of total emissions. We use a nested grid version of just model with just file metrology, and the black carbon radiative forcing is calculated using RTMG that had been coupled with the just model. We performed the one control simulation and the file sensitive simulation to quantify the contribution from emission sector in China. Another emission with LBC emission in China turned off to quantify the contribution from non-China emissions. Here we show the model evaluation for surface species concentration. The left column is for seasonal mean, the right for annual mean. And a scatter plot of the simulations and the observation is shown in the bottom. We can see our model could well capture the spatial and the signal variation of the observed concentration, but there is also a low bias of about 30%, for the annual mean. We also evaluated our simulated black carbon absorption ALD using retrieved ironized BC ALD following the method of bound. Through our sensitive simulation, we can have the contribution from emission sectors and non-China emission. We can see that residential and the industrial sector are the two main contributors, especially in winter. Residential sector contributes about 6 micrograms per kilometer over eastern China and the Sichuan Basin. We can see that non-China emission have small contributions, less than 0.5 micrograms per kilometer. Here we also still simulated the outside black carbon radiative forcing at the top of the atmosphere. We can see large signal and the spatial ocean over eastern China, and in winter, BC radiative forcing over eastern China and the Sichuan Basin could reach as high as 8 to 10 watt per square meter. Here we show the contribution to black carbon radiative forcing on the annual basis. We can see that BC radiative forcing from residential is 0.44, from industry 0.27, from non-China emission is 0.3. The domestic and the non-China emission contribute 75% and 25% to BC radiative forcing in China respectively. And the boundary transport in spring is the largest contributor. We also see the percentage contribution to BC radiative forcing over different regions with different here. Over high emission regions, North China and Southwest China, we can see the percentage contribution could reach as high as 20% and 40% respectively. Over South China, the percent contribution is as high as 60%. Is 6%. Here we show the summary, and the residential sector has the largest contribution to surface black carbon by 5 microgram per kilometer in winter, and by 1 to 3 microgram per kilometer in summer. Industry contributes 1 to 3 microgram per kilometer to BC contribution. BC radiative forcing over China is 1.22 watt per square meter, and the domestic and non-China emission contribute 25% respectively. This result will have important implication for taking emission measurements to mitigate the near-term climate warming and to improve air quality in China. And so I will stop here and have time for your questions. Thank you for attention. Yeah. Yes. Yes, of course. And from our simulation, we have a small high value for DLF in China to compare the other simulations. Okay, thank you.
That's your contribution from non-China sources
Yes.
in spring is essentially biomass burning in Southeast Asia.
Yes, especially in spring from South Asia, biomass burning emissions.
Good question. Okay, great. We've shaved 4 minutes off the overall session record, so take back to that. We have, if I can ask the poster presenters presentation to come down and just say a minute or so on each, 1 minute on each way. Half a minute on each. So if you can come down and just tell us about your poster very quickly.
Hello, my name is Ivan, comes from University of Nebraska-Lincoln. I give the poster introduction for Xiaohong Xu. The dust emissions have much uncertainties. They are determined by some parameters, for example, source function and threshold fraction velocity. Our question is, can we constrain these parameters rather than emissions through inversion modeling? Welcome to the poster. Thank you. This one is. Hello, this is my poster. For the uncertainty of SO2 emissions, we use the OMI SO2 observations as constraints for inversion of SO2 emissions of China. And the posterior SO2 emissions can be applied to the corresponding month for the next year. Thank you.
Okay, thank you. Hi everyone, I'm Hansen Cao from Peking University in Zhongwei Foods Group. We combined the Galinsol and formaldehyde vertical column density observed by GOMI2 instrument with the GeoSchem adjoint model to inverse the non-methane VOC sources globally. We also quantified the emission uncertainty using a deterministic method. The optimized aspirin emission globe was about 50% higher than prior evaluation. If you want to know the details, come to my poster. Thanks.
Hi, my name is Jiayue Huang from University of Washington. So we are trying to improve our constraint on the CISA aerosol emissions within the GeoSchem. Currently, the CISA aerosol emissions from the open ocean by the wind stress is the only source in GeoSchem. But there is study indicate that the CISA emission can be produced on the sea ice surface, mainly by wind blowing over salty snow or frost showers. So I have added that emissions from the sea ice surface into the GeoSchem. So if you're interested in that, please come check out. Thanks.
Sorry. My name is Le Kuai from UCLA. My poster is about flux inversion of carbonyl sulfate using satellite measurement from tests. Carbonyl sulfate is a trace gas composed with oxygen, carbon, and sulfate. It is an important potential tracer for photosynthesis. Because its dominant source and sinks is completely separate spatially, and it's a one-way flux for the vegetation uptake. The long-term observation of the OCS has no trend, so suggesting global budget has to be balanced. The recent study finds the vegetation uptake need to be revised upward so that the seasonal cycle can be well simulated. The main question is what's the additional source to balance the global budget? If you are interested to find out where is the missing source, please stop by my poster. Thank you.